Good evening, good evening, good evening. This is your Captain Shreyas on the PWJ English channel and welcome to the chapter 1 of your 12th standard physics for your JEE preparation of 2027. Welcome all my dear JEE 2027 warriors. Hi Harsh, hi Extra, welcome Toshi, welcome Sirthik. Looks like I am audible and visible to all of you. Amazing, amazing. So now, let me tell you what we are exactly going to do. It's a big class. Obviously, we are starting at 6 o'clock, but it's going to extend for a decent amount of time. I don't know how much, but let's say 4 hours. Okay. And the intention is to clear all the concepts from this particular chapter of electric charges and fields. And we will do all the theory from NCERT, but we will be also doing the JEE mains PYQs as well as some JEE advanced questions, so that you guys get a clear-cut picture of how to solve the questions and also understand the concepts behind every single topic. Okay, so yes, we are going to go through the NCERT flow, or you can say the NCERT topics, because that is the prescribed syllabus by NTA for JEE 2027. But the problem solving, the concepts, everything will be obviously much higher than the board level, and we are going to go deep into JEE. So that is the agenda for today. I hope you guys are all excited, and a lot of you are asking for these detailed lectures, a proper big class, kind of a marathon, but not exactly a small one like a one shot quick revision. This is not a revision class. This is right from the basics, right from the scratch for a 12th standard student, assuming your 11th standard basics. So let's begin with the lecture, and I hope you guys are doing great. Hi Raghavan, hi Sankaresh, hi Shri. Good evening, good evening, good evening, my dear lovely warriors. So time to begin. Now, in this particular chapter of electric charges and fields, this entire thing deals with the concept of electricity and the basis of electricity, because the next, the third chapter after this is going to deal with current and electricity. And before that, you need to understand what charges are, what charges do, how do they repel, attract each other, what kind of energy is associated with them, and how the behavior changes in different medium, and then how can we store this energy in a device called capacitor, which is the chapter 2. So this concept of electrostatics has been developed very recently. It's not like it was there during the time of Pythagoras or Socrates or something like that. Last 200-300 years, barely people have started understanding this concept, and in the just last 100 or 200 years is where a lot of formulas, a lot of concepts, and a lot of ideas and formulations have happened. Now, we discuss in this particular chapter what is the meaning of charge, what is this force which is there between these things called as charges. And by the way, these are the charges which are there in your atoms, and atoms make up molecules. Molecules are there in all the things around us, including you. You at the end of the day are atoms, right? And these atoms are held together by these electrical charges, which you would have studied in the chapter of atomic chemistry, atomic structure in chemistry, right, in the 11th standard. So my dear warriors, we're going to start with the concept of charges, then the force, and then this new thing called as field. You might have a bit of an idea from 11th from gravitational field, but it's okay even if you don't know it. And then, we'll slowly go on to dipoles and other things as well, and potential, etc. So, let's start. Now, usually this chapter is also called as electrostatics. What is the meaning of the word static? What is the meaning of the word static? Static means stationary. That means at rest. So, whatever you will see happening over here, the charges will be stationary, or if not stationary, they will be moving at very negligible speeds, or their speed effects are neglected basically. So they are considered stationary, because when they begin to move, when the charges begin to move, that means they go into dynamic nature. that means they are in motion. And when charges move, understand it is nothing but called as the current, electricity current. So when you turn on a fan, when you switch on the light, or when you are watching anything on your computer, there is electronic circuits or electrical circuits. Those carry electrical current through those wires. That electrical current is precisely the motion of charges, which is charges in dynamic nature, electrodynamics. That is chapter 3. But we are restricting right now in the first and second chapter to only stationary charges, static charges at rest. Or even if they move at low speeds, we are neglecting those speed effects. Is this absolutely clear? Thank you for all the love from Tamil Nadu. Yep. Awesome. Yes. Alright. Like I said, the duration will be easily, 4 hours or even more. Who knows? Alright. Great. Now, let's understand about these electrical charges. These electrical charges, how they come and what are their numbers associated, what are the signs, etc. So, you would have done this experiment definitely in school or at home or with your friends somewhere. You take a comb, rub it on your hair, and then it starts attracting bits and pieces of paper. Sometimes you rub some material on some another material, and you will see because of that what happens is you are able to attract or repel some other material. So what is this happening over here when you are rubbing things? When you are rubbing things, something magical is happening in these bodies, and these bodies are developing a new property called as a charge, or they are getting something like an electrical charge. And these rubbed bodies, when brought to another body, which is either charged or whatever, they start applying forces on each other, and they might either attract or repel depending on something called as charge. So this entire concept of rubbing and pulling or repelling things is based on this concept of electrical charge. Let me give you simple examples. Like I told you about rubbing a comb on your hair and then attracting bits and pieces of paper, that is one example. But the most scientific examples which you will be studying are the ones of glass rod being rubbed with a silk cloth or something. So if you take a glass rod, if you take and rub it on a silky cloth, okay, silk cloth, then you will see that the glass gets something called as a charge, electrical charge, and an exact opposite behavior is created on the silk one. So if the glass gets something called as a plus, then the silk gets something called as a minus. If you call glass as minus, then the silk will get something called as a plus. That plus and minus quantities are the signs of the charges. Instead of a glass rod, you take a plastic rod and rub it on a silk cloth, then it is found that the plastic gets a negative value of a charge, and the silk develops an exact opposite, which is then the positive value. And then let's say, for example, you have taken a glass rod, rubbed it on silk, it has got a positive value in it. Another glass rod, you have rubbed it on the silk cloth, that also has a positive value on it. And if you bring these two glass rods together and leave it, you will see they will start going away from each other. They will start going away from each other. So two identical glass rods which are rubbed on the silk cloth, they start going away from each other. Same way, if you take that plastic rod, rub it on that silk cloth, another plastic rod, rub it on another silk cloth, and bring those two plastic rods together, they too start moving away from each other. That means both plastic rods or both those glass rods had a similar kind of thing which caused their repulsion, because both glass rods are identical. Those similar things began to repel. Similar plastic rods began to repel. But if you take a glass rod and plastic rod which has been rubbed already, and then you bring them together, then they start attracting each other. That shows that when things are opposite in nature, they begin to attract. So this was a very famous experiment to prove that you have two kinds of charges and similar identical things will repel, whereas opposite things will end up attracting. Like plastic and glass will attract if rubbed already, but plastic repel, glass repel. Is this clear? Is this concept clear? How this was understood? Now if you take some another rod, maybe some metal is there, I don't know, some random metal is there, you rub it, zzz, and then you get it. I don't know what charge is there. Let's say I bring it close to glass rod and I see it repels, but if I take close to plastic rod, it starts attracting. What can I comment about the sign of this mysterious metallic rod? Can you guys quickly answer in the chat box? Yes, any board, any person can watch this video, my dear warriors, because gradually scaling up to JEE level. That's the whole agenda. Yeah, I take this rod, mysterious rod, I bring it close to glass rod, I see it starts repelling. But I take this mysterious rod and bring it close to plastic rod, zick, it starts going close to the plastic rod. It starts getting attracted. Yes, that means, I'm going to talk about induction, don't worry Divyesh. Yeah, that means it started going away from the glass rod. That means it has the same kind of thing as the glass rod, which is positive, and it got pulled by the plastic rod. That means it has the opposite kind of thing as the plastic rod. So negative on the plastic, so metallic rod confirms that it still has positive charge. Is that clear, everyone? So that is how you can predict what kind of charge is there, whether it is the same or whether it is the opposite in nature. So this famous experiment, very important. Sometimes they can just ask you a very laddu question on it, but very rare on it. Now another concept over here. What will happen if I take that glass rod and rub it on that silk rod? Now glass is positive, silk is negative. Now I bring that glass rod which is positive and again slowly move it on that silk cloth. All the charges which were there will slowly disappear. It's gone. It's neutralized. Yes, things can also get neutralized. In fact, it can so happen that if I have a metallic rod which is positively charged like the glass one, and I have another rod which is negatively charged like the plastic rod, and this positive metallic rod and this negative metallic rod, I bring it and touch it to each other, I will see they might end up neutralizing each other. The positivity and the negativity will end up cancelling and they both might become uncharged. Uncharged meaning there is no charge in it. There is no net positivity or negativity in it. Sir, how did you decide whether glass is positive or whether plastic is negative? Nobody has to decide. You can arbitrarily choose anything as positive and anything as negative. It doesn't matter. It doesn't really matter. Okay, by convention we are just going with it. So I think that line is there. Yeah, over here. Yeah. So this concept was first discovered by, Benjamin Franklin. You might have heard that name, very familiar it sounds. So it's just a convention that we happen to choose that, okay, whatever is there on the glass rod, I don't know, it is nothing but, positive. Or even the cat's fur. I mean, if you take a meow meow cat and if you rub, you will see it also develops a positive charge. Whereas the one on the plastic rod or on the silk was considered negative by convention. Later on, after a couple of 100 years, people understood, oh, this charge is coming from the atom. Oh, inside this atom, there is a positive thing and a negative thing. Oh, this negative thing is electron and it goes around this positive thing. Oh, that positive thing is proton, which was discovered by Rutherford's experiment. Electron discovered by J.J. Thomson in another experiment. So, these things were discovered much later. Who is bringing that positivity? Who is bringing that negativity? Was not clearly understood by Benjamin Franklin. They at that time thought some magical electric fluid is there which goes from one side to the other side. If both positive and negative are there in equal amounts, it is neutral. But that fluid, if it exceeds, then it becomes either positive or it becomes negative. So they called or they thought of some kind of mysterious electrical fluid, but no such electrical fluid exists. It was nothing but electrons and protons which are there inside the atom at the end of the day. Is this absolutely clear? So this was just by convention, understand? Benjamin Franklin, who basically thought about the concept of charges and positivity and negativity. Okay, very clear. Shankareshwar, Kinjim, Satyamaki, man, first concentrate on the class, man. Yeah. Okay. Now, yeah, this is also standard. This was also concluded via these experiments only. So these experiments concluded that if you have opposite kind of charges, they will attract, and if you have similar kind of charges, they will repel. Very, very important. So I can easily show over here, this positive will repel from this positive, or this negative will repel from this negative, but you will see this positive and negative will definitely attract each other. So this was your repulsion, they repel, whereas this one over here, they are ending up attracting each other. Opposites will attract, like things will repel. That was one of the most important conclusion. Till this point, absolutely clear, very simple laddu things only. Okay. Now, you might think, sir, what if an object has no charge? Well, then it has zero value of charge and then it is said to be electrically completely neutral. If an object possesses an electric charge, then it is said to be electrified or charged. But when it has no charge at all, when it has no charge only, there is no positivity, there is no negativity, then it is said to be neutral. But if it has either positivity or negativity, doesn't matter, then you call that yes, it has been electrified or it has been charged. Now whether it is positive or whether it is negative, doesn't matter. Both cases I will say it has been charged. As simple as that. Okay, great. Now you might be wondering, sir, how can I predict whether this object is charged? Should I go near it and will I get pulled zoom or will I get pushed away? That's how I understand. No, that's not the real test of, or it's not so easy to predict whether it has charge or not just by whether it is attracting you or repelling you. Okay, because you yourself might be charged and maybe because of that you are attracting it. So this, ambiguity comes. Maybe I am attracting because I am charged. So maybe that was not charged at all. So that is why you use a very particular device called as the electroscope, the gold leaf electroscope. Yes, this simple apparatus to detect if the body is charged or not is called as the gold leaf electroscope. Why do we need this device? You need to understand that. Like I said, if I want to detect somebody's charge or not, just going near that thing will not guarantee, even if I am pulled or pushed away, attracted or repelled, it does not guarantee that object is charged, because I don't know whether I myself am I charged or not, because maybe I am the reason causing some charge on that body, I am the reason I am affecting that other body, and that is why I am attracting or pulling it. So naturally, is that body charged or not can't be detected by just that attraction or repulsion. This is a very common sentence, can be asked as assertion reason. Attraction and repulsion of two bodies is the real test of a body being charged. The answer is no. Attraction and repulsion is not the real test whether a particular body is charged. Rather, you need to use this device. And what is this device? You have a metallic probe or a metallic rod which partially is outside and partially is inside a chamber made of glass. And that rod finally bifurcates into two small thin threads or leaf-like elements, which are suspended. Normally those leaves or those threads, you can say, because of their own weight, they are slightly heavy, not very heavy. What will happen? They will just end up touching each other, because imagine if two things are hanging from the same point, they will just hang because of their own weight. They will come like this and they will sag and they will just end up, being very close to each other. Is that right? So under normal circumstances, two things suspended from the same point due to their own weight will come down like this. That's what is going to happen here. Now imagine you bring somebody, I don't know what it is, and I touch to this end of this metallic rod. By the way, this cap is completely insulating, else what will happen? The charges might end up going somewhere else only. I don't want that. Anyways, so I bring somebody and I end up touching it. So if I see that these two leaves or threads start going away, then I will be sure that this body was charged. How? Because whatever charge is there, I don't know, positive or negative, I don't care. But if there is some positive or negative charge, that will go via this metal. Metal is a very good conductor. We'll talk about conductors and insulators in a bit. And you will see that the charge will go here also and here also. If it was positive, this and this both will be positive. If this body was negative, this and this both will be negative. Which means positive will repel, negative and negative will also repel. So that is why you will see these two leaves will start repelling and they will start pushing them away. But if it was not charged, nothing will enter, nothing will be charged over here, no repulsion nor attraction, those leaves will stay like that. So touching the body should repel those leaves, and that's the simple litmus test, you can say, for detecting if a charge is there or not. It can't predict whether it is positive or negative, but it can only say if it is charged or not charged. Is this absolutely clear? Is this absolutely clear, my dear warriors? What a gold leaf electroscope does? Can it detect the sign of the charge? No. So this is very, very important. It can't detect the sign of the charge. I don't see whether it is written over here. It's an indicator of the amount of charge. Yes, like if the charge is less, it will repel only so much. More charge is there, so it will go like this. Lot of charge, it will go like this. So how much it is repelling will decide how much charge was there. Very little charge, it will not move so much. More charge like this. Even more charge, it will go like this. That's what will happen. So it can't decide the sign of the charges. The sign of the charges. If you want to decide the sign, then you do one simple task. You touch this body to the electroscope and you see, oh, it is reflecting. Okay, great. It is charged. Keep it aside. Bring another body, touch it over here and see what is happening. Oh, it is again moving like this. Great. This is also charged. Now bring those two bodies together and see what is happening. Attracting, opposite. Repelling, same kind of charge. So that's how you can predict whether the signs are same or opposite in nature. Is this clear? So that's how the sign gets decided after you get to know whether it is charged or not. If I touch the body and see there is no charge, then there is no point of determining the sign. Making sense? Okay, great. So sir, what is that thing which actually decides whether it is positive or negative? What is that thing which makes one positive, which makes another thing negative? And that thing is nothing but the motion of the charges within those bodies, and particularly it is the electron. Later on people discovered it. Long time back people did not know about this. People understood that it is the electron which transits from one body to the other body when you are rubbing, touching things. Because if you talk about the atom, guys, the nucleus should always stay intact, because that decides the chemical nature or the properties or characteristics of that element. The atomic number comes from the nucleus. So it's never the protons or the neutrons detaching from the nucleus. because that is always intact, it's strongly held, it's a very compact thing inside the atom. It's those electrons which keep revolving in that atom. Those electrons, they can be plucked, I mean not literally like a flower, but they can easily eject, they can easily jump, they can easily be acquired from one atom to the other atom, of one body to the other body. So these electrons jumping from one body to the other body creates that unbalance. It's like you had lots of Pandus and Champas. Let's say for example, Champas are positively charged, Pandus are negatively charged. Champa is positive, Pandu is negative. Usually the balance is maintained. We have nice number of couples, Pandu, Champa. 5 Pandus, 5 Champas. 5 Pandus, 5 Champas. 10 Pandus, 10 Champas. How much ever positive, that much ever negative. More positive, more negative. So the balance was maintained. But let's say the Pandu decides, I'm going to ditch Pandu, the negative one. So Pandu leaves a Champa. In a group of, let's say 10 couples of Pandus and Champas, one of the Pandu, breakup happens and leaves. So what will happen in that system? You will see there are more Champas and less number of Pandus. So the balance has shifted and you will see it will be more positive. It will be more positive than negative. So the balance will shift. It will become more positive than negative, guys. But on another day, again those 10 couples were there, all equal Pandus and Champas. The Champa gets angry and leaves. Champa was positively charged. So the positive went away. The positive went away. Then again the balance shifts. You can visualize this. The more negative will be there and less positive will be there. So whenever a positive or a negative charge either leaves or comes, you will see the balance will shift, and that's when the body becomes a positively charged or negatively charged. Right now this pen, me, you, this table, this board, yes, they are all having equal Pandus and Champas, equal positivity and negativity. So it's all electrically neutral, perfect balance. How much ever positive, that much ever negative is there. How much ever positive, that much exactly negative. That balance is there in the nature. When God created, when nature created itself, however, there were equal number of protons, equal number of electrons. But what will happen when you rub things, these electrons will migrate from one body to the other body. That's it. That shifts the balance. Either it will become positive or it will become negative. But it is always the electrons which migrate from one body to the other, and it is never the positive charge. That's what you should understand. Is this clear, my dear warriors? Yes. I'm so glad, Pratap, you're loving these classes, and I'm glad that you have chosen to take a drop and watch these classes, continue these classes right from here. Okay. Alright. Arnab, Shri, perfecto. Amazing. So, when we say a body is charged positively, that means it has lost electrons. So that's why it became more positive. But when we say a body is charged negatively, that means it has acquired those electrons. Got it? So, sir, how is it that whenever I take a glass rod and rub on silk cloth, how is it that always the electrons decide to leave the glass rod and go to the silk cloth? Because silk becomes negative, glass becomes positive. If glass has become positive, that means electrons left them. How? Why, sir, electrons went from glass to the silk? The reason comes from this particular paragraph or these lines. So, if you see clearly, when we say body charge, we always refer to the solids. Since some solids, some of the electrons being less tightly bound, and that's how they are transferred to the other body. See, this is that important line. Meaning, if you go back over here, glass was not holding those electrons properly. It's like saying Pandu and Champa were together, lots of Pandus and Champa were together. Another beautiful Champa was walking by. This Pandu overlooking his girlfriend, started looking at that other Champa, and slowly that Pandu walked away. This relationship was not strong. That was the problem. Not holding that Pandu together. Pandu the electron, Champa the positive charge. So Pandu the electron, the negative charge, slowly drifted to the other Champa. That's how that became negatively charged then, that particular body. Alright. And this body now became positively charged because you're not holding it properly. So the affinity, the attraction, the closeness of that electron to that nucleus decides whether it will be held or whether it is okay for that electron to leave. Sometimes some other atom might give like a lollipop, might say, hey, you come to me, hey, you come over here, things are very beautiful, things are great. So that's when this electron will migrate to the other body. So the silk gives better opportunities to the electrons as compared to the glass, and that's why the electrons leave always the glass and end up shifting to the silk. But in case of plastic, it's the opposite way. Plastic says, oh, silk, hold on, I'll give you better opportunities than that. You come to me. So the electrons migrate to the plastic rod and they end up leaving the silk cloth. So plastic has more affinity, better attraction towards the electrons as compared to the silk, and that's why this migration happens. Is this absolutely clear, my dear warriors? Why this migration happens? So when we say that it is charged positively, that means it has lost some of its electrons. Similarly, when we say it is charged negatively, then it has definitely gained some electrons. Okay, absolutely clear? Amazing, awesome, perfecto. Let's do some questions coming up on your screen, and here it is. A silk cloth is rubbed on a glass rod. Then the mass of the glass rod will. What do you think? A silk cloth is rubbed on a glass rod. What do you think, guys? Come on, answer this particular question. Okay. If you want, you can also participate in these polls, using the Pylons app, and it's fun. If you're watching it through the Pylons, you can watch the same class. You can even ask doubts to our AI. You can also get notes ready-made through our AI generated, models. And of course, you can also participate in the polls and be in the leaderboard even after the class. So make sure you are using the Pylons app, and you can also compete with each other using this. All right, it's absolutely free of cost. Okay, and you can watch any YouTube video using this. So silk cloth is rubbed on a glass rod. Glass becomes positive, silk becomes negative. So glass has lost the electrons. If glass has lost the electrons, that means electrons, whatever mass it had, I know it is very small, but it had mass, that mass went to the silk cloth. So in this process, glass lost the mass of the electrons. So the mass should reduce. So option C, I believe. Yes, very good. Option C. Amazing, amazing, amazing. Correct. It's only because this particular glass rod will become positive. It's because these electrons have migrated to that silk cloth, This was your glass. So because of that, the mass of the electrons is gone. It's gone to the silk. So mass of silk will increase, mass of glass will decrease. So will it change in kilos or grams? Not at all. It will be so small that you will probably not be able to even feel it, sense it so easily. You need a very, very sensitive scale, or there needs to be a mass migration happening out there, which is very, very rare. Okay, great. Now that we understand this, let's go to the concept of conductors and insulators, and then I will be helping you out with conduction and induction. These are two important things which you should know. What are conductors and insulators? Simply put, if you connect a battery and you see current flows, it's a conductor. If current doesn't flow, it's an insulator or a bad conductor. Very easy way of looking at it. So there are some objects which readily allow the passage of electricity through them. If they allow the passage of electricity to them, then they are called as conductors. Like copper, aluminium, humans, animals, metals, basically. Even we are conductors. That's why we get a shock Else we would be cool, right? Why would be worried about shock or putting our hand somewhere else, right? Even animals get electrocuted. So metals, humans, animals, basically most of the biological things are conducting in nature. So you will see when connected to a battery, there is a beautiful flow of charges, and this flow of charges is what runs those appliances, bulbs, motors, fans, etc. Okay, that is what a conductor is. But obviously an insulator like a brick or a stone, when connected to a battery, you will not see the bulb getting enlightened because there is no passage of charges through that stone, wood, thermocol, whatever it is. So things like porcelain, plastic, nylon, wood offer very high resistance to the passage of electricity, and that's why they are called as insulators. That's why they are called as insulators or bad conductors. You will see after a couple of chapters, in fact the last chapter of 12th standard, it is neither an insulator nor a conductor, it's somewhere in between. It allows, but it is so small that you are wondering, what is this allowing? Should I consider this as an insulator? Should I consider this as a conductor? It's something very much in between. It does not completely block, but it does not pass also so much that you can run a bulb and you will use it as a wire. So that is then called as a semiconductor. That's a completely different game. We will discuss that in the last chapter of physics of 12th standard. Okay, as simple as that, right? Great. So having talked about what is a conductor and an insulator, one very good example of a conductor and insulator. This is so relatable, I am pretty sure you have experienced this. You touch a doorknob or you shake hand with someone and then suddenly you have got some kind of a shock, a static. You touch a metallic object or a railing, you get a shock. Have you experienced this? Have you experienced this? Yes, no. Shankareshwar, if you have wasted 11th, don't worry about it. 11th classes will come later. But for now, do not lose focus of your 12th. That's what I told you in the 12th roadmap. 70-80% of your time for 12th, remaining 20-30% of your 11th. Right? Have you experienced this? I'm pretty sure you would have. So what happens over here is that whenever, let's say you are sitting on a chair, you are moving, shaking hands, moving hands here, there, rubbing. Your cloth, the chair fabric, everything is of some cloth material, maybe wool, silk, whatever. So that rubbing action, what does rubbing action do? Makes you a charged body, and you are a good conductor. Humans, animals, metals, they are good conductors. So now you have got charged. Now the charge is there in your body. But where will that charge go? It's there only. It is not going anywhere. Now you shake hand with another person, and the moment you shake hand, immediately this conductor finds another conductor, and these charges are like, hooray, let's go, and they all start going through your hand to the other person. So there is a passage. Our hand acts like a wire, and the other person's hand also acts like a wire, and there is electricity flowing between these two hands. That's why you got a shock, and you're like, oh, wait a minute, what is this? So the charges accumulated within your body have suddenly found a passage via your hand to another conducting body. That's why you get that shock. So is there a way to avoid this shock? Actually, it's not practically feasible, but let's say you are wearing rubber slippers. You are wearing rubber slippers, then 100% you will get a shock when you touch another person. Why? Rubber is an insulator. So the charges can't go anywhere. There is only one way outside your body. Where are you touching anything else? You are not touching anything else normally, right? Only your feet are on the ground. So the feet was touching the ground, and ground can absorb those charges. So if you are directly standing on the ground, all those charges would have gone into the earth. It would have gone into the earth. So there will be nothing left on you. So when you meet someone, already you have no charge, so nothing will happen. But if you are wearing rubber slippers, plastic shoes, any nylon material, anything, that's a bad conductor. So all the charges get accumulated. So then when you touch another conductor, you will get the shock. Sir, but I remember my teacher telling me you should wear rubber slippers when you are touching electrical appliances. Absolutely right. Your teacher was not wrong at all. I am just saying that you wearing rubber slippers stores the charge within your body, or rather does not allow any charge to pass within your body. So it just stuck over there. But when you touch an electrical appliance, now you don't have charge, the electrical appliance has a charge. By mistake, you happen to touch some live wire. The live wire will say, oh, I found a conducting body. So the current will start flowing within your body. And if it sees, oh, the feet are connected directly to the earth, you're just standing on the ground, the live wire will allow that current to flow within your body, through your legs, directly inside the earth. You become a part of the electrical circuit, which you don't want to be. You will get electrocuted, you will get shock, it is fatal. But if you have a rubber, then that current sees, oh, this is a conductor, but wait a minute, I can't go anywhere, so no point going through this body. So that's why you are safe, because that rubber acts like a block, or complete like a dam for a river. Okay, it stops that electricity and it does not flow within your body. Is this clear? So you better wear rubber slippers or plastic shoes, whatever it is, because it is usually considered safe, unless you are not okay with getting that shock when you touch each other, which is okay, which is fine. Okay, yes, is that clear? So what about the pigeons sitting on electric wires? That is a completely different concept. I will talk about it in current electricity and Ohm's law. That's got to do with that, not this concept. But of course, you cannot ask pigeons to wear shoes and fly, and oh, you're sitting on those wires, oh, be careful, don't put this fit on this wire, this fit on this wire, oh, you will get shocked. No, you can't do that. But that's another concept, we'll talk about it later. Now, let me talk about, where did this go? Not this. This conduction and induction. So when you talk about methods of charging, when you talk about methods of charging, there are basically two types of methods. First is, imagine you have a body and you have another body over here, doesn't matter what it is, and let's say this body has some charge. This body maybe has a charge, does not have a charge, doesn't matter, but some other body is there. Now, if you find that you touch this particular body, and then you find the charges get redistributed. So the charges get redistributed. So there were some 1, 2, 3, 4, 5, 6, 7 charges. Maybe, the charges got redistributed like this. 1, 2, 3, 4, 5, 6, 7. Okay. Then I will say the charges have flown within the body. The charges have flown within the body. So the charges flow from one body to the other due to contact. So the positive charge has gone from this body to the other body. So there is a conducting path, either through a wire or through touch. Maybe you take a wire and connect them, that's also okay. So there is a conducting path. That's why this method number 1 is called as charging via conduction. So you touching something or you connecting via wire, then the charges get redistributed. That is charging via conduction. Okay, that's what happens. But the other method, the second method, is called charging via induction. Oh, what is this, sir? Induction. So in this case, imagine there is a charge body and then there is another body. Okay, so this body has some charge, maybe like this. Right now they are really far away. Right now these two bodies are really far away. They are really far away. Now you bring them closer, but ensure that they don't touch. Ensure that they don't end up touching each other. That's very important. Now, what will happen? These charges have nowhere to go. They will still stay here. But now, since they are close by, nearby, now these positive charges will start attracting the electrons within this body. Yes, the electrons within this body. So you will see these positive charges from these atoms. These electrons will start coming on this side and they will end up leaving an equal amount of positive charges on the other side. If this was negatively charged, then positive will come on this side, negative will come on the other side. These charges have come from this same body, but now they are at two different places. So I will now say this body has been polarized. What will I say? This body has been now polarized. Polarization, meaning it's like saying there is a classroom which is fully united, very nice, healthy friendship is there. Suddenly one teacher comes or some other person comes and starts, talking nonsense about other kids. This student is talked about this student, that student is talking about other student. So everybody starts making groups. So there is a polarization in the class. The classroom became polarized. So two polarities have been created, two groups have been created. So that is the meaning of it. So this is called as induction and these charges are called induced charges. So there is positive induced charge over here, positive induced charge on the far end because of this, and there is negative induced charge on this side, induced charge on the other side. So you will get positive and negative induced charge. So the difference between induction and conduction is whether it is touching or not touching. It's like you come to learn from me and I say, okay, don't worry, my dear son, here you come. I take my hand and put it on your head and all the knowledge gets transferred into your head. That is conduction. But then another day you come and I'm like, okay, don't worry, my dear, I will teach you everything. So I just like, okay, yes, you just sit here and I am using my powers and your brain is getting all that knowledge. That is induction. It's a very hypothetical example. Don't take it literally, but just to give you a feel of what conduction versus induction is. Is this clear? Got it? Everyone? Yes. Yes, Kamaleshwaran, we are completing all the concepts. Got it. Got it, Shankareshwan. Very good. How can, sir, can we know that every concept? JEE Advanced Zone, I just mentioned, yes, we are completing all the concepts, right? Great. Now, there is a funny thing which happens. Which I won't want to tell. And this is one of the most interesting examples, I would say. When you talk about conduction or induction. Let's say, for example, you bring a neutral body. What is this? This is a neutral body. And let's say this is a charged body. Whatever charge is there doesn't matter. Charged body. The question is, will there be a force between them of attraction or repulsion or no force? I will give you the options. Option A, there will be attraction. Option B, there will be repulsion. Option C, there will be no force at all. What do you guys think about this? I'll give you 30 seconds. There is a charged body and there is a completely neutral body. No charge, no net charge. Neutral means positivity and negativity is equal. That's it. So, what do you think will happen? Will there be attraction? Will there be repulsion? Or will there be no force? Come on, think about it and answer through the Pylons app. If you have not downloaded it yet, please download it. It will be useful throughout the lecture series, not just for my class. Okay, plus obviously smart notes and PYQs, everything. All right. Okay, if you have not yet downloaded the app, oh, by the way, you can also use it on Chrome as an extension. Yeah, Chrome also gives this as an extension. Some people are saying A, some people are saying C. Well, you will be shocked to know the answer. You will be shocked to know the answer. The answer is always going to be A, irrespective of whether it is positive, whether it is negative, irrespective of that. Okay? And it doesn't even matter whether this is a conductor or even if it is an insulator, doesn't really matter. The answer is always attraction. That's why I told about this some time back. You might have thought it's a very small or a trivial thing. So what is this electroscope, sir? Chumma, use no two charges, see if they attract or repel. That's enough. No, that's why I said attraction or repulsion is not the true test of seeing if a body is charged. That's why you use a gold leaf electroscope. This example, whatever I just asked, this question is exactly going to prove the same. How? I will tell you. Let's assume some charge is there. Doesn't matter what charge, assume some charge. Let's say I take negative charge. It doesn't really matter. What will this negative ask? This negative will see, where is positive? Oh, let me all pull it towards me. So looks at this atom, or sorry, this body. It has so many atoms, so many positive charges, but atoms, positive charge, nucleus can't move. So the nucleus can't come there, but electrons are there. Shoo away. So the electrons are shooed away, booed away. Electron repulsion. So the electrons will start repelling each other and they go accumulate on this side. So when they leave their respective atoms, what will you see? An equal amount of positive charge to be developed. Oh, crazy. So now what will happen is, you will notice a very interesting thing. This positive charges will get attracted by these negative charges. This negative charge and this negative charge will get repelled. But mind it, these negative charge and negative charges are far away. So the repulsion due to the large distance, far away distance, is smaller. So there is smaller repulsion, but positive and negative, they are close by. So there is stronger attraction. Because of this net force, this is big, this is small, you will see the net force is going to be like this. So there will be net attractive force. Hence, the answer to this is always going to be A. Is this clear, my dear warriors? Why this happens? Even this was positive, this will be negative. There will be stronger attraction, and this positive will have weaker repulsion. So net attraction will always be there. Crazy concept? Yeah. So this is very, very interesting. A normal neutral body can also get attracted. So that's funny actually, because we always think only opposites will get attracted, but that's not true. But keep in mind, if this was also neutral, this was also neutral. Imagine two no charged bodies, then they will not do anything. Obviously, it's not like magically this positive and negative will, oh, let's come close, let's go far. No, nothing will happen. Then there will be no attraction nor repulsion. That clearly tells there is no charge on it. Okay, perfect. So moving on now, talking about the properties of charges, very straightforward. Properties of positive, negative and neutral charges. There are, remember, only two signs of charges. The third one is having neither of them, which is then called as a neutral charge or a zero charge. The example of a negative charge is an electron. The example of a positive charge is a proton, and the example of a neutral particle is a neutron. Sir, are these the only three things? Answer is no. There are other quantum particles which have positive and negative charges. Like you will study in the chapter of nucleus, there is something called as a positron. Like electron is negative, positron is the size of the electron but of opposite charge, basically positive charge. Then photon, not proton, photon is neither positive nor negative, it is a neutral particle behavior. So yes, there are other particles which fundamentally will show either positive, negative or absolutely no charge. Now, a lot of students, and I know a lot of people also mention this, they say a neutron is made of proton and electron, and that's the most random, wrong concept which many kids learn. Many people think neutron is made of positive and negative charge, that's why it is neutral. Wrong. There is no equal amount of positive or negative. Rather, I would say there is no charge only on it. There is a difference between saying there is equal positive and negative, that's why the net charge is 0, versus saying actually there is no charge. So neutron or photon, or which is a particle of light, all of them have literally no charge in them, neither positive nor negative nor in equal amounts. Getting my point? So that is what that neutron or neutral particle is all about. Great. So let's talk about the properties of charges. First property, which is very, very important, very simple. If there are multiple charges in a body, then the total charge of that particular body is simple the sum of all the charges on that body, Q1 plus Q2 plus Q3. So the total charge of that system or that body is a simple addition of all the charges. Is a simple addition of all the charges, and the reason why you can add them is because they are scalars. A lot of people think, sir, charge has a sign, positive, negative, positive this way, negative that way. Wrong. These are wrong things which are there in your head. No, just because something has a sign does not mean it is a vector quantity. It does not mean even it has a direction. It's just that it has a sign. That's it. It's a value. It is positive or negative. It is not positive means right, negative means left, nothing like that. So it is a scalar quantity, and scalars can just be added without worrying about the direction, right? Now, keep in mind, charges also have a number associated with them and a sign associated. So when you add, take care of the sign. Meaning if something is negative, take that as a negative number and only then add them. Alright. So that is something which you need to keep in mind. Mass of a body is always positive, whereas the charge can be either positive or negative or even 0, like I said. So let's take an example. Say, if I tell you there is a plus 2 charge, then there is minus 3 charge, then there is minus 4 charge, there is then 0 charge, then there is plus 1 charge. So if I take them as a system, how much total charge is there? You just have to take these values and just keep on adding them. That's all. That's all. Just keep on adding them. So 2 plus minus 3 is 2 minus 3, which is minus 1. Minus 1 minus 4 is minus 5. Plus 0 is still minus 5. Minus 5 plus 1 is minus 4. So the total charge on this system is basically minus 4. Same way, guys, if I tell, okay, I have plus 7, then I have minus 3, then I have plus 2, I have plus 1, I have minus 6. These are the charges within a system. Then the total charge of that particular system, just add these numbers. 7 plus 2 is 9. 9 plus 1 is 10. 10 minus 3 is 7. And 7 minus 6 is 1. So the total charge on this body is basically plus 1. That's how you add the charges, just like scalar numbers, accounting the signs also. That is very, very important. Simple. So that is a simple first property, which is the addition of charges, like a regular addition. The next is also a simple thing, which is the conservation of charges. Whatever charges, net charge our universe has given, it always remains the same. Now forget the universe. If I have even an isolated system, the meaning of isolated is it's unaware of what is happening outside that boundary. So neither heat can enter, nor light can enter, nor an object can go out, nothing can go out, nor can come inside. It's perfectly isolated from the outside world, right? It's like it's in its own cocoon. So in such an isolated system, whenever there are charges, whatever redistributions might happen, this negative will jump there, this positive will go here, atom will split, bomb blast will happen, nuclear explosion will happen, whatever happens, doesn't matter. You will see always that the total charge of that isolated system is always conserved. This is called as the conservation of charge. Total charge in an isolated system is always going to be conserved. Very important, it is not possible to either create or destroy the net charge. No matter what, you cannot magically create extra positive, extra negative, or you can take out negative or take out positive. Not possible. Okay, very, very important. So just to give you some examples related to this. In some nuclear reactions, you will see that there will be a neutron, and that neutron will emit some kind of radiation, but at the same time it will emit a positive charge. It will emit a positive 1 charge and it will emit a negative 1 charge. This is called as a proton, and this is nothing but an electron. If you notice, earlier there was 0 charge on this. There was 0 charge on this. You can see this is 0. This was neutron, right? Now also if you add the charges, +1 and -1, it is still 0. So on the LHS side, it is 0. On the RHS side, it is +1 plus -1. It is still going to be 0. LHS equal to RHS. Similarly, imagine there are charges like this, +2, then there is -3, then there is -1, and then there is +4. Okay, this is some random system in which, you know, all these charges are there. Now some charge distribution happens, and you know, I find that this particle now has +5 charge. I find this particle now has -2 charge. I find this particle has -1 charge. How much charge will be there on this? How much charge will be there on the 4th particle? You don't have to break your head so much. Just see LHS and RHS. First see how much charge is there on the LHS. 2 plus 4 minus 3 minus 1. How much will it be, guys? 2 plus 4 is 6. Minus 3 minus 1 is -4. So it will be basically +2. That is the amount of charge which should be there on the LHS side. Now let's assume whatever missing charge is there, I'll assume it as Q. I don't know what it is. Add all these charges, it should be the same. So if you see on the RHS side, my dear warriors, there is 5 charge, then there is -2, -1 and Q. So this will become basically 5 minus 2 minus 1. Minus 2 minus 1 is -3. So 5 minus 3 is nothing but 2. So 2 plus Q charge will be there. So this and this should be equal. This and this should be equal. So because of that, because this LHS and RHS should be equal, it just proves that Q has to be 0. So there is no charge on this particle to conserve the charge. That's how you can predict how much charge will be there in any missing body. Is that clear, everyone? Coincidentally, it comes out to be a perfect 0. Randomly, I chose the value and it came out to be 0. Okay, that's simple charge conservation. You will see there are a lot of laws which are there later on which are based on this simple principle. It looks very trivial, no? But later on there are complex circuits which can be solved using these simple principles. And that was developed by Kirchhoff. You will see it in current electricity. Okay, great. So that was conservation of charge. All right. Now the third important property is the quantization principle. It talks about everything which is charged is always a multiple of a fundamental elementary value. You cannot have random values of charge. It always has to be multiple of something. Say for example, the government decides that only 500 rupee notes will be printed and be official. Nothing else is going to be allowed. New monetization policy. Okay, chumma randomly I am making this up, guys. Okay, only 500 notes are allowed. Nobody can even talk about 10 rupee notes, 1000 rupee, 2000 rupee, nothing. Okay, only 500 rupee. So, can you buy an item worth 1200 rupees? Illa, right? You will be like, Poda. Go, what are you telling? 1200. I can't give you 1200. Either 1000 or 1500. Can you buy something worth 57 rupees? No. 50 rupees. Can you say 50 rupees, sir? So this is 500 rupee note. I will break it into 10 parts and you take 1/10 part. One tight slap I will give. So that also not possible. So you can give 1 lakh rupees, you can give 2 lakh rupees, 1 crore also possible because they are all multiples of 500. But you can't trade 1200 or 50 rupees or 57 rupees or even 600 rupees, 501 rupees, 499 rupees, not allowed. 10,000, 20 rupees not allowed because they are not multiples. So universe, when it made charges, see how beautiful it is. It said, I am going to give you an elementary particle and that elementary particle is having a charge of E. Now anything which is charged will be 2e, 3e, 5e, 7e, 8e, but negative is also possible. So minus 2e, minus 3e, minus 4e, minus 5e is also possible. But anything which is a multiplication, pure integral multiple of E. Anything else? Not allowed. Anything else? Not allowed. Hi Vibix, my name is Captain Shreyas. Is that right? Okay. So any charge is an integral multiple of E. That is what quantization of charges, where n is any integer, positive or negative. Integer means positive and negative, right? Not a whole number. And yes, the basic unit of a charge, which is there on an electron or a proton, and that value is taken as E. That value is taken as E. Is this clear? So it can be any multiple of E. It cannot be fractional multiple of E. Sir, what is that value of E? I'll tell you that. That value of E is basically 1.6 into 10 to the power minus negative 19. Negative 19 Coulomb it is. 10 to the power minus 19. Sir, how did they get this charge? See, that is SI unit. That's not your worry. So, you know, there is a proper definition of this in current electricity, how this unit comes. Oh, by the way, charge is not even a fundamental quantity. It is a derived quantity. Not many people know this. Yeah, many people think charge is a fundamental quantity. Wrong. Charge is a derived quantity. Units and dimensions. Derived quantity. And the value of charge is basically current multiplied by time. So it is basically current multiplied by time. Current is fundamental. Time is fundamental. So that is what it is. So strictly speaking, the dimensional formula of charge is ampere raised to 1, time raised to 1. Ampere raised to 1, time raised to 1. That is the dimensional formula. That is the dimension of charge. That is the dimensions of charge, ampere raised to 1 into time raised to 1. So it said that if for 1 second you pass 1 ampere of current, then the amount of charge flown is basically 1 coulomb. That's how it is being defined. So that and all we need not worry about. But yeah, this is basically the amount of charge which is there on a single electron or a proton. So the SI unit of charge is basically called as a coulomb, and it is denoted by the symbol C. In this definition, 1 coulomb is when you have in 1 second 1 ampere current flowing. The amount of charge which goes in 1 second due to 1 ampere of current is called as a coulomb of charge. Okay, and remember the exact value of E comes out as 1.602192, but you don't have to remember these decimals, just 1.6 is enough, into 10 to the power minus 19. Now the thing about these small values, because negative 19 is a very small value, it says that even if you have 100, 500, 1000 electrons, this will still be of the order of minus 18, minus 17, minus 16. Which means if you talk about a single coulomb, it's a very big unit. Huge. In fact, a coulomb of charge, if you count it, there will be roughly 6 into 10 to the power 18 charges. It's insane. It's a huge number. This much charge, this much collection of charges is nearly impossible, or rather I would not say impossible, it's very difficult at a normal human scale. Yes, it can happen at lightning or natural phenomena in volcanoes and lava and all of that, but very difficult. You need very extraordinary forces of nature. So a coulomb of charge is a very big unit. We generally don't find things about that scale. So usually you will be seeing microcoulombs, millicoulombs is also very huge, picocoulombs, nanocoulombs. That's the scale which we will be dealing at. So at this scale, the charge, is very, very small value. So that is very small at atomic level. So you cannot really get a coulomb of charge very easily. Okay, so generally you will be talking micros, nanos and picos. Okay, that's the scale at which you will be discussing the charges. Is that clear? Current is fundamental. Yes, got it. Perfect. Now, one last thing over here. Because this is so small, no? So when I roughly say 2 coulombs of charge, there will be so many charges in it that I won't worry about whether it is a multiple of 1.6 10 to the power minus 19 and all of that. So at a larger scale, we really don't end up checking whether it is satisfying this relationship. But if the charge is small, very, very small, then I need to be sure that it is mathematically possible. It is mathematically possible. Otherwise, see, if I tell 500 rupee notes are the only notes which will be printed. For a person like me who will have 10,000 rupees in the bank account, for me, 1,500 goes or 1,500 comes, I will be worried, no? Yes or no? If I have 10,000 rupees only in my bank account, then I will be worried. But somebody big is there, Ambani is there, Elon Musk is there, Bill Gates is there. They have huge amount of money. 1,500 or even 10,500 rupee notes goes in or out. Will they be worried? No, right? So, at a very large scale, we really don't worry about this changes or whether it is an integral multiple or not. For a very small scale, like Papa Shreyas Sir, 500 rupees goes in or out, I will be like, today I should eat or not. Like that it will be. Yes or no? Okay. This is just to give you an example, guys. Don't worry, your Shreyas Sir is very, 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 very rich at heart because of your love. Thank you so much. Okay. Great. So, let me see if you can think, is this charge possible or not possible? 1.69 into 10 to the power minus 19 Coulomb. Is this possible or not? 1.5 into 10 to the power minus 19 Coulomb. Is this possible or not? 1.6 into 10 to the power minus 18 Coulomb. Is this possible or not? What do you guys say? Come on. Is this possible? Definitely not, because you can clearly see this is not any number into 1.6 into 10 to the power minus 19. So this is definitely not possible. 1.6 into an integer will not give you this. How about this? Even this is not an integer into 1.6 into 10 to the power minus 19. So even this is not possible. But this number definitely 10 multiplied by 1.6 into 10 to the power minus 19, definitely possible. This 10 is an integer, so this is possible. The third one is possible. Yeah? Oh no, I don't have a BMW, man. I don't have a BMW. Unfortunately, Sir does not have BMW. Okay, so that is what it is. So let's begin with some questions coming up on your screen. Here it comes. Which of these charges are not possible which of these charges are not possible? Come on, think carefully. I cannot, okay, multiple choice. All right, start the poll. Oh, more than one option is correct. Huh? More than one option is correct. Think, which of these charges are not possible? 1.2 10 to the power negative 19, 4.8 10 to the power minus 19, 8 into 10 to the power minus 16, 19 into 10 to the power minus 19. Mohammed's, even I won't be doing derivations as such for JEE perspective so much over here. So apart from the derivations, we'll be doing everything else. And the time is up. Oh, 1 second, guys. What happened to my AC? Which of these charges are not possible? A is not possible for sure, and B is possible, C is also possible, D is also not possible. Let's see how many of you marked it correctly. A and D, yes, this is what it is. And by the way, this is our leaderboard till now. Come on guys, more guys need to participate in these polls. Okay, so yes, A and D are the correct answers, because you can see this number is definitely not n times of E. Even this number is not n times of E. But if you see, this is 3 times of E. Can you see that? 1.6 into 3 is 4.8. 16 3s are 48. Same power. What about this? This is also possible. How do you get that? Well, you know Q is equal to N into E. So N will be Q divided by E. Just check this. Charge is 8 into 10 to the power minus 16. And this is 1.6 into 10 to the power minus 19. 16 5s are 80, right? So 1.6 into 5 is 8. So this is 5. And this is 10 to the power 3. So basically this is nothing but 5000 times of E. 5000 is an integer. So B and C are possible. A and D are not possible. The question was, which of the following is not possible? So in case you ever wanted to find how many numbers are there, you divide the charge by E, you will immediately get the number of charges within it. Is that right, everyone? Just say for example, the question was, how many charges in let's say in 6.4 into 10 to the power minus 17 Coulomb, if this was the question. What will you do? Q is equal to N times of E. So N will be Q divided by E. The charge which I am talking about is 6.4 into 10 to the power minus 19. E value is 1.6, 10 to the power minus 19 over here. So 16 4s are, so 1.6 4s are 6.4, and this will become 10 to the power positive 2. So basically the number of charges are 400. So there are 400 charges which totally make up this many coulombs of charge. So that's how easy it is to figure out the number of charges. Now let's see another question based on this. A sphere is charged to 3Q. It is touched to another identical sphere whose charge is negative Q. Now, what is the charge on each sphere? That's the question. This is a single correct question and your poll timing starts now. Think about it. Think about it. I'm very good, Ragul, and thank you so much, Lord Standard. Yeah, I'm so glad that everything is very, very clear. Awesome, awesome, awesome. Okay, let's do this. Sphere to plus 3Q and another identical sphere with negative Q. Now, both of them will touch each other. So, the charges will get redistributed and eventually they should have identical charges because we are talking about identical spheres here. So, each sphere will have an identical amount of charge. How much will it be? Hint, use the conservation of charge. That's it. Use the conservation of charge. So, here are the two spheres. So, after touching, what will happen? Let's see. Okay, we'll mark the answer, but don't worry, before that, there is plus 3q charge here, and then there is minus q charge here. If you talk about the total charge on the system, it will be positive 3q plus negative q, which is basically 2q. So the total charge should remain conserved. It should remain conserved, isn't it? This charge should remain conserved. So now both of them should have equal. So positive 2q, how will it distribute? Plus q here, plus q here. What is the total? The total is still going to be plus 2q. Is that right? Plus 2q. So each sphere has how much charge? Yes, it has just plus q of charge, and that is the answer. Very good. 100% of you got it correct. Amazing, amazing, amazing. Very nice. Option A. Excellent. Yeah. Very good. So that was all about it. So till now, whatever we have studied. Oh, by the way, I'm also putting the summary pointers which are there at the end of the class. I'm just putting it up after every subtopic that I'm covering here, so that we don't have to go through summary at the end again. So I'm just showing it to you over here. So let's go through all the things. Electric magnetic forces are going to determine atoms, molecules and bulk matter. Very true. Because these charges which are there within the atom, how much charge is there, how many protons, how many electrons, what are the forces, that decides the chemical composition, the characteristics, the nature of every single thing. Carbon has different protons, oxygen has different protons, different properties. Yeah. So that's how it is. From simple experiments, frictional electricity, one can infer that there are two types of charges, like they will repel or they will attract, they are unlike or they are like. By convention, we took glass as positive and plastic as negative. Remember that experiment, taking that rubbing things, rubbing a comb on your hair? Yeah, it transfers the electrons, negative charges, from one body to the other body. And why did they leave? Because one body was not able to hold it, other body was able to attract it very beautifully. So that's why the charges migrated. One became positive, one became negative. We saw similar signs repel, opposite signs attract, and you can give anything as positive or negative, but we had to give something or else there will be confusion in different parts of the world. So we said, okay, glass rod always will get positive. So everything else according to it. If you are repelling to a glass rod, opposite, so you are negative. If you are, repelling means same. If you are repelling from a glass rod, so you should be same charge as a glass rod, that means you will be positive. But if you are attracting, so you should be opposite. So that's why you will be negative then. So everything was determined based on the attraction or repulsion from a standard entity like a glass rod or a plastic rod. Conductors conduct electricity, insulators stop the electricity, right? And you will see that in electrolytes, both positive and negative ions move. Like if you dissolve salt in water, there is Na plus and Cl minus ions which are there, and that's how you will get positive charges going one side, negative charges going other side. Whereas in a copper or aluminum conductor, it's only the electrons which are jumping, taka, 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 they are going from one place to another. But protons are intact. But in electrolytes, positive sides will go one side, negative sides will go other side. So both motions are there. Electric charge has three basic properties. First is being scalar, so you can add them. Second, it is conserved. Third, it is always an integral multiple of it. Now, many people take addition of charges as a very normal thing. It is not like it's okay, but actually addition, simple addition means that it is a scalar quantity. So it is scalar, that's why it can be added, or it is added, that's why it is a scalar. A lot of people get confused. Assertion, reason, statement, or statement 1, statement 2. Which of the following is true? Charges are scalars, that's why they can be added, or charges can be added, that's why they are scalars. What do you think? What do you think? Very simple. Huh? This can be your statement question. Statement 1, statement 2. Which of the following is correct? And in H.C. Verma also, this statement is there in points to ponder or, conceptual questions, short answer questions. What do you think? A lot of people tell me, sir, because a charge is a scalar or anything is a scalar, that's why you can add them. And that, my dear friend, is absolutely incorrect. Okay? Just because something is a scalar, that's why you can add it is wrong. It's rather the opposite. Because you are able to add them, hence it is a scalar. Hence it is a scalar. Okay? So, a lot of people feel it's the other way around. The same is also true for vectors. Because forces can be added by the laws of polygon or triangle or parallelogram, hence it is a vector. Not the other way around. It's not a privilege. It's not a privilege. Rather, the onus of proving it's a vector or a scalar lies with the physical quantity. It's like guilty until proven types. Okay? So, any physical quantity comes, it's not naturally, oh, you are a vector, you are a scalar. Huh? It's not a privilege. It's rather the burden of that physical quantity that, okay, I have to prove whether I can be a vector, whether I can be a scalar. Oh, let me add. Oh, I add with the laws of scalars, simple addition. I am a scalar. Oh, I add with the laws of polygon or triangle. Oh, I am a vector. So, it is the other way around. Is that clear? Yeah. Sanju, good evening, my dear. Okay. So, these are small things, but matter a lot on how you understand physics. Anyways. So, conservation of charge means total charge remains unchanged with time. This means whenever bodies are charged, there is a transfer of charge from one body to the other, but no creation or destruction, which makes sense. If I rub something, if this develops -5, this body will develop +5. If this develops +6, this will develop -6. Always conserved. Never ever there is an exception. Okay. Shall we now go to Coulomb's law? Yeah. It's up to you, Ekaf. It's up to you. Okay. Now we are coming to the main thing. Okay, Coulomb's law. Funnily, many of the forces, fundamental forces of nature, have a very similar trait in their behavior. Like how two masses attract, how two magnets attract or repel, or how two charges attract and repel. Their behavior is very similar, but also slightly different. Similar in formula, different in the variables, the the alphabets that you will use or the constants that you will use. Like when two masses attract each other, Newton was able to prove this. He was able to observe things and he was able to derive a law called as Newton's law of gravitation, which said two masses attract each other with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Same thing is also true for even magnets and even charges. Let's focus on charges for now. If you have two charges, then they will either repel if they are alike, or they will attract if they are unlike or opposite. And that force of attraction or repulsion, that force of charges of attraction or repulsion is directly proportional to the product of the charges. The Coulomb measured the force. Coulomb measured the force between two charges and found that it varied inversely as the square of the distance and directly proportional to the product of the charges. And directly proportional to the product of the charges. Very important. And it always acts along the line joining the two charges. This statement sometimes feels very trivial. Sir, what is this? Obviously along the line only, no sir. Two charges are there. Why will the force act like this? Why will the force act like this? It's mad or what? It sounds very simple, but I don't find that it is very natural, because you will see in magnetism, there will be a charge, it's going somewhere, pavam fellow, the force on it suddenly will go somewhere else. Suddenly some random direction that force will be. There is a current carrying wire, the force on it will be somewhere else, neither in the direction of current nor in the direction of the field. So it's not very obvious why it should be there, and if you go deeply, you can probably argue about it, why it should be always along that line, but let's not worry about that in so detail. But remember, it is always along the line joining, either like this or like this. It's never off the track, or never like this and like this. No, it's never like that. It's always along the line. This is experimental. Why it happens, nobody knows. Now, because I just said Coulomb's law, in Coulomb's law, that force is proportional to the product of the charges, and that force is inversely proportional to the square of the distance between them. Hence, therefore, that force is proportional to the product and inversely proportional like this. So, if I want to get rid of that proportionality, I need a constant over here, and then I will put Q1, Q2 divided by R square. This is that constant of proportionality that was given later on, not by Coulomb. Okay, and this constant is of the value, this value of that constant is 9 into 10 to the power 9, positive 9. 9 into this constant is 9 into 10 to the power 9 SI units. That's why the formula becomes K, constant, charge multiplication by the square of the distance. How it looks so similar to gravitation law, G m1 m2 by R square. Yeah, very similar to gravitation. Even in magnetism, the formula looks very similar, but let's not go there. Okay, is that clear, everyone? What is this K called? That K is often called as the Coulomb constant. What is this K called, guys? It is often called the Coulomb. Why Coulomb? Because that person only gave that law, so we'll call it Coulomb's constant, not Shreyas constant. Correct? So Coulomb's law, so we call that constant also as the Coulomb's constant. Very simple. 9 into 10 to the power 9. Later on, you will realize that this K, which is your Coulomb constant, is often written down as 1 by 4 pi epsilon naught. You will be like, sir, why not 2 pi? Why even pi? Where did this pi come from? What is this? Don't worry. You will understand it after I explain you Gauss's law. Not now. It comes from Gauss law, nothing else. What the hell is this epsilon naught, sir? E with a naught, epsilon naught. This is called as the permittivity of vacuum. Permittivity of vacuum. What is this permittivity of vacuum? Don't break your head now. But remember, it is that number which decides how medium will affect this force. Yes, this Coulomb force between charges gets affected by what medium is there around it. Is it air? Is it some other gas? Is there nothing at all? Is there water? Is it placed in mud? Is it placed in stone? It decides the number epsilon naught, and that decides whether that force is as strong as before or not, because when the medium changes, the force generally changes, and you will see the force will usually become weak. Yes, so this number is the permittivity of vacuum. If it was not in vacuum or in air, then it will be permittivity of stone, permittivity of something else. So it depends. It depends. So right now this value can be easily found out, because we can see 9 into 10 to the power 9 will be 1 by 4 into pi. Pi is 3.142. okay, into epsilon naught. Solving this, you will get the value of epsilon naught, which comes out approximately 8.85. So if you want to find epsilon naught, rearrange these numbers into 10 to the power negative 12. 10 to the power negative 12. Okay. So the units are exactly opposite of it. So it will be basically Coulomb square per Newton meter square. That's it. That is the value of permittivity of vacuum. Of glass will be different. Of water, different. Of some other medium, different. But yeah, vacuum and air are roughly the same thing. Air is almost vacuum, only somewhere here and there you get molecules. Yeah. So it's almost like vacuum. So the value of permittivity for air is roughly 8.85 only. It's not very different. Like refractive index, you remember? Refractive index of air is 1, almost same way, just like that. Is that clear? Very, very good. Excellent. So these are the things which you definitely should remember. This is permittivity of vacuum. It's a medium dependent property. We'll not worry about it right now. We'll be focusing only on vacuum and stuff like that. So this constant K is usually put as 1 by 4 pi epsilon naught. Same thing what I told you just now. Okay, just now. So let me just, I think this is there over here. Yeah. So this expression gives the force between charges in vacuum, but if they are placed in some different medium, then the situation gets complicated due to other matter and permittivity changes. So epsilon naught is also, this is vacuum, is also same roughly for air, but epsilon of another medium is different. Okay, this is what you should understand. Great. Now let me show you one simple example before I go ahead. And let's see, at atomic scale, what is the force on an electron due to a proton at a distance of let's say 4 angstroms, at a distance of 4 angstroms. This is a very good question and you will see why in a bit. So we have an electron which is obviously negatively charged. We have a proton which is obviously positively charged. They will obviously end up attracting each other because of opposite charges. There will be a force F, and yes, these have to be equal and opposite, Newton's third law. It can't be more and less. There is no ego clash between them. Oh, I am positive, oh, I am big, nothing like that. They always have to be equal but opposite and on different bodies. Third law of Newton. Now this force can be easily calculated magnitude wise, is the Coulomb's constant K into charge 1 which is positive, charge 2 which is negative, but we are only going to take magnitudes, remember that. So E into negative E divided by distance square. Now let's start substituting the values. Coulomb's constant 9 into 10 to the power 9. Charge value 1.6 into 10 to the power negative 19 and also 1.6 into 10 to the power minus 19. I am not using negative because mod is there. If you remember carefully, there was mod here because we are only interested in the magnitude. Direction is obvious, whether attractive or repulsive. So we never bother so much of direction because that can be easily figured out. Okay, the whole thing divided by r square. R is the distance, 4 Armstrong. Now Armstrong is negative 10 power. So what will happen? This will become 4 into 10 to the power minus 10 and square of it. So square, right? 4 into 10 to the power minus 10 square. Let's see what do we get. So this will become 9. 1.6 I can write it as 16. This also I can write it as 16. So 16 multiplied by 16. This power 9 is there. If I write 16, this will become minus 20. Because I've shifted the decimal here, this will become minus 20 and minus 20. So 10 to the power minus 20 and 10 to the power minus 20. Great. The whole thing divided by 4 square, which is just 16. Is that right? And this will become 10 to the power minus 20. Now the calculation looks straightforward to me. One of the 16s gets cancelled. I can also see this minus 20 and minus 20 gets cancelled. So I'm left with only 16 nines, which is 144. So 144 into 9 and minus 20, that's going to make it minus 11 Newton. Is that right? So that is the force between them. Now look at the value of force. It's so small. It's so small. Value of epsilon has to be remembered, Shankareshwaran. Yeah, you have to remember it. Yeah, this is so small. Then you might start wondering, am I even studying it right? Why do we even need to study it? Sir, such a laddu force, sir. Such a small force. Minus 11. 0.000000144. What is going to do? Hey, headache only. Sir, leave it. Chumma, you are wasting your time. Yeah, a lot of people feel that. Until I do the next calculation. And I say, forget the force. What is the acceleration of that electron? So then you start wondering, oh, what am I saying? This electron is there. There is a force on it because of which it will accelerate. And of course, the electron has a mass. What is the mass of an electron? Well, the mass of an electron is close enough to 9 into 10 to the power minus 31 kg. Very, very laddu mass. Oh, now things start making a difference. Is it? How, sir? By Newton's law, F is equal to mass into acceleration. So acceleration is force by mass, sir. Yes. What is the force, sir? Force, we just got it, 144 into 10 to the power minus 11. 144 into 10 to the power minus 11. What is the mass, sir? 9 into 10 to the power minus 31. Oh my God. 9 goes with 144 16 times. So this is 16 into minus 31 and 11. 31 minus 11 is 20. So it becomes 10 to the power crazy. This is crazy. Crazy acceleration, guys. So yes, the force might be small, but you also need to look at who is this force applied on. It's a bichara, Pavum electron with a very, very small mass. So for that Pavum electron, that force is huge and it produces insane acceleration and motion. And that is the reason why we study it. Is this clear? Is this clear, everyone? Yes, definitely, Chandresh. Watch my roadmap strategy video. I just gave it a couple of days back. Yeah. If you want to write it in minus 9 also, you can write 1.44 into 10 to the power minus 9. It's one and the same thing. Yeah. This is also crazy amount of acceleration. So that's the reason why we study it. Now there is also a vector form of this equation, which is given in your textbook. Let me explain that rather than just showing it to you. It's very simple. Not many times you will get questions on this. So if there is a charge q1 and then there is a charge q2, instead of writing the distance between them as r, what I do now, I write that particular distance between them as r12, distance between r12 or r21. Now if I write bar over here, then it means slightly something different. R21 bar is nothing but position vector. There is a bar, that means it's a vector of 2 with respect to particle 1. Where is 2 as seen by 1? I am 1, 2, 2, 2. Oh, you are there. So that is your position. So I'll show it as a position vector. Then R21 cap is a unit position vector. unit position vector, and these have their standard formulas if you remember. Yes, R21 cap is R21 bar divided by the magnitude of that particular vector, R21 magnitude. Yeah, that's standard formula, unit vector formula, which you have studied in vectors chapter 11th standard. So this is something which you have studied back in the 11th standard. Okay, now if you ask me the force, I will always show it outwards, but this time I'll write force on 2 because of 1, and this is force on 1 because of 2. Notice how they are equal and opposite. Why? Is because of third Newton's law of motion. F21 means force on 2 due to 1. This is force on 1 due to 2. Force on 1 due to 2, force on 2 due to 1. That's how that nomenclature goes. So if you look at the magnitude of the force on 2 due to 1, it is just simply given by your Coulomb constant, that means 1 by 4 pi epsilon naught, then the product of the charges, great, q1, q2, and whole thing divided by distance square, that means we are talking about R21 square, R21 square. This is simply put the magnitude information. This is simply put the magnitude information. Is that right? But if I want the directional quantity, the vector quantity, then the only thing which will be different is 1 by 4 pi epsilon naught will be there. You will also put q1 and q2 as it is over here, but over here after this you're just going to put R21 cap. Why? Look at this direction, look at R21 cap. R21 cap is a unit vector like this. R21 is a unit vector in this direction of the force. So this is giving the direction, this much is giving the magnitude, so this becomes the vector itself. So I don't have to worry about this anymore, and I then look at it like this. This much gives me the magnitude of the force. This tells me the direction in which the force acts, and this is the entire vector of the force. This is the entire vector of the force. So this is often called as the vector representation of that particular force. Vector representation of that particular force. Is that clear? Very simple and laddu thing it is. Just a vector formula instead of normal scalar formula. Alright, cool, awesome. So I think it's time that we solve some questions, and here it is, very interesting question coming up on your screen. This was asked in JEE Mains 2021. Come on, do it. Everyone, I want everyone to think about it. A charge Q is divided into two parts and then moved apart. There is some force. When do you think it will be maximum? So what should be the ratio? What is happening? You had a charge Q. You broke it into two small parts, small q and the remaining Q minus Q. Now there is some distance between them. Okay, great. There is also some force which will be there. Now I want to make sure that this force is maximum. What do I do? I'll give you a hint. Think like this. Let's say this is Q1. Let's say this is Q2. So what will that force look like? Force will be that Coulomb constant. Yes, R square will be there. And on the top, you will have Q1, Q2. Is that right? Now the question says, I want the repulsion to be maximum. So I want this particular force to be maximum. How can I make it maximum? I can't change this. I can't change this. The only thing I can change is their product. So I will make their product maximum. How do I make sure that their product is maximum? Well, look at it. If you add these two charges, you should get back the original charge by conservation of charge. So capital Q is nothing but Q1 plus Q2 by conservation of charge. The sum of two numbers is a value which is fixed. I cannot change this. I can change how much this is, how much this is. If this was 5, this can be 2, 3 or 3, 2 or 1, 4 like that. So I can change the distribution, but from the original source I am dividing it. So sum of two numbers is constant. And what do I really want? Q1, Q2. Q1, Q2, which is their product, has to be maximum. Product is basically maximum. And when is this going to be? The product is maximum when Q1 equals to Q2. Basically, the numbers are equal. Numbers are equal. This is always true. This is also AMGM property which you learn in mathematics. So basically, when the numbers are equal, that's it. That's it. The product is maximum. I'll just give you an example. Just imagine this number is 5, okay? So how can I divide? 1, 4, 2, 3, 3, 2, 4, 1. Take the product. 1 into 4, 4, 2, 3s are 6, 3, 2s are 6, 4, 1s are 4. But if I make it 2.5 and 2.5, if the numbers are equal, yeah, what will it become? 6.25. 6.25 is the maximum of all these numbers. Can you see that? 6.25 is maximum of all these numbers because it was exactly divided into half. So this is true every time, guys, by the way. So hence, it's very obvious now what should this ratio be? Capital Q and small q. So if this is 2, this will be 1, half of it. So 2:1, which means answer B is the right answer. Answer B. Is that clear? Very good, edit, Sapna, Shri. All right, very good. Oh no, I'm not frustrated. I was just giving that entire property because not everyone might remember it, forgotten, wasted 11th, backlogs, 100 reasons. Got it? So that's the reasoning behind it. Next, this was in JEE Mains 2022. Two identical conducting spheres carrying charges 4q and minus 2q are kept at a certain distance apart. The force between them is F. Now they are briefly connected with a wire. Remember conduction method? Wires you touch, charges get distributed, conduction method, right? Same thing. Then you again bring them back to their original place. What's the new force between them? All right, let's solve it. And meanwhile, I'll also start the poll in case you want to answer it. Okay, the poll is also running. I'll explain coolly. I'm not going to be in a hurry. Okay, so I'm not competing with the poll out there. Okay. Neither should you unless you know this before. Okay, so we have charges 4q and minus 2q. So obviously there will be some kind of attraction between them. And that force will be given by K divided by R square Q1 Q2. That means 4q into 2q. Magnitudes only. So it will become 8K Q square divided by R square. Is that right? That is the force before. All this was before. Now, what happens? You touch them. So the moment you touch these charges, the charges will get redistributed. 4q and negative 2q. Total charge will be positive 2q. Correct? Plus 4 with negative 2 will become plus 2. Simple mathematics. So the total charge looks like a double omelette is positive 2q. That means each charge will be plus q plus q. Oh, now you again bring them back. Q over here and q over here. What's the distance? The original distance only. Sometimes in some questions they change the distance also. So now there will be some kind of a repulsion between them. I will call that force as F prime. F1, F0, F nu, whatever you want to call it. So that F prime, that new force will be Coulomb constant Q1, Q2 divided by same distance. Wait a minute, KQ square by R square, I know from here, in this before situation, just look at it guys, KQ square divided by R square, take that number 8 below F, it is F by 8. Oh, so it's just F by 8 is the new force. Hence, it will be option B. Is that right, everyone? Yes, option B. Let's have a look. Perfect. Option B is correct. Pakka? Yeah, it's not D. Yeah. All right. Ayo, you don't know this technique. Ayo, I discovered this long time back. Who is it? Lancelot Whitey. So what students do, very smart students, and this has been going on from long time, from COVID era I think. So they tell the parents, I am studying, I am watching Shreyas Sir, PW, this, that, any lecture, YouTube you open. But actually what they are doing, their lecture is open, they are not listening to anything, or even if they are listening, they are not bothered. They are busy searching something or flirting with someone, or maybe you are calling each other and deciding, okay, listen, I can't use WhatsApp. Today there is this live stream and we'll join, over here at this time. You also be there, huh? They all are connected in the school or whatever, coaching, God knows. And they all come and they will chat, not bothered, and they will continue. So don't worry about them. Okay, it's a new parallel universe which is running, which you should not be bothered. Yeah, for real, right? So I know this from long time. Now you guys don't use this method because just because I leaked it or just because I told you. Yeah. All right, great. So let's go to the next one, which is the forces between multiple charges, which is very straightforward actually. So what happens if there are many charges? Imagine there is this papa charge Q, and earlier there was only one other charge, let's say Q1. So what will this Q1 do? This Q1 will say, okay, you are at this distance, okay, so I'll apply this force on you, maybe your same type of charge, so I'll repel you, and that force I will call it F1. But then suddenly you place another charge over here, I call it Q2, maybe the sign is opposite in nature, so between these two charges there will be attraction, and then maybe this force will be like this. This value will be completely different, F2. Then another charge comes, and that is, let's say, Q3, and that distance is like this. So it might apply some other force, and let's say that is F3. So on and so forth. Hundreds of other charges are there, and Qn is the last charge. So all these forces are acting simultaneously on this charge. So what will happen? A result of all of these will be a net force which will be coming. This will be the net force on whom? That small q. But due to Q1, Q2, like that till Qn, other charges. So this is the net force on small q due to this, all the charges together. And this net force, needless to say, is strictly speaking the vector sum of all these forces. So if you do vector sum, law of polygon, law of triangle as needed, if you add all these forces, you will get the net resultant force. This simple law is called as law of superposition. This simple law is called as law of superposition. So if a single charge is there, other charges will all apply their own respective forces. If you take the vector sum, that's it. That will give you the net resultant force. Like over here, this is repelling this, and this is also probably attracting or whatever repelling this. So if both of them are there together, then you will see there will be a resultant force. I think the sign is wrong or direction is wrong, one of them. This should have been like this, or else it can't repel. So this will repel, this will also repel. Red and blue together is giving this yellow resultant force. So due to a number of charges, the vector sum of all the forces due to other charges taken one at a time, individual forces will be unaffected. This is termed as the principle of superposition. This is termed as the principle of superposition. Okay, great. So let me take an example out here. This was asked in 2020. Very simple. Three identical point charges, each of charge q, placed at the vertices of an equilateral triangle of side A. The net electrical force experienced by any one of the charges is. Okay, let's start. Start with a pole. Okay, 45 seconds starting now. Start by drawing a triangle. Okay, this is your triangle. Great. Draw the charges q, q, q. Is that right? Okay. Side is A. Side is basically A. So force on any charge, because they are all identical, it will be the same. So if you take this charge with this charge, they will repel. Same like charges will repel. So it will be like this, isn't it? And at the same time, this and this will also repel. So it will be like this. But since magnitudes, distances are same, forces will also be same. So this will be KQQ divided by A square, which is technically KQ square by A square. Same magnitude will be there over here, KQ square by A square. But that is not the total force. Total force will be the vector sum of them. The vector sum will be somewhere in between like this. That is the net force. For that, just check how much this angle will be. Well, this is an equilateral triangle. So internal angle will be 60 degree. Needless to say, even this being opposite will also be 60 degrees. Is that right? This will be also 60 degrees. So just use vector addition formula. F is nothing but root of KQ by A square plus A square plus B square plus 2AB cos theta. Remember that vector formula, KQ square by A square whole square plus 2 into KQ square by A square, KQ square by A square and cos 60 degrees. Don't get scared. KQ square by A square is common everywhere. Bring it outside the root. It will just become KQ square by A square. Inside the root you have this 1, this 2. These two, when you take it outside, it will just become the single one. Cos 60 is basically half. Is that right? So 2 into half is 1. 1 plus 1 plus 1 is 3. So this will become KQ square root 3 divided by A square. Root 3 I can see in option C. That is the right answer. So if I had to mark, I'll mark answer C. Very good. Most of you got it right. Congratulations. Good. Understood? Yep. A square plus B square plus 2AB cos theta. Yeah, you can use parallelogram law, triangle law, but geometrically solving it is much difficult. Using this analytical formula is much simpler. Okay, let's do the next one coming up on your screen. As you can see, this was again based on superpositioning principle. Here is the next one. Two charges are separated by some distance. A third charge is placed on the line joining them such that the entire system is in equilibrium. The position of this third charge from this charge is where? 2019 pre-COVID question. Let's draw the diagram. Without that, we can't understand. 2 point charges separated by L. Okay. So, separated by L. 2 point charges. Q and 4Q. Perfect. And this distance is L. Now, there is a third charge placed on the line joining them such that the entire system is in equilibrium. You need to start thinking, where should I exactly put the third charge so that they are in equilibrium? So, I feel maybe we'll draw a bigger line now, just so that we get a neat diagram, or else it will look like full khichdi only. This is L. Now think, where should another charge be placed? Right now this Q and 4Q will 100% be repelling each other, needless to say. So there is repulsion between them, and that repulsion is how much, guys? K, Q, 4Q divided by L square. This is also K, Q, 4Q divided by L square. So this is repulsion, because sign is same, no? Plus Q and plus 4Q, repulsion. Somehow I want it in equilibrium, meaning this Q should be opposed by this force in the opposite direction. How can that happen if there is another charge over here? So what should happen is that next charge will be somewhere here, I don't know, charge from the charge plus Q, okay, maybe over here. A third charge is placed on the line. Jennings says that it is the entire system is in equilibrium. Now that third charge is not given to me, I'll call it as minus Q, and of course this negative charge, what it's going to do is going to pull this over here, and it's going to pull this over here, and this will also experience same force on both sides, so it will also be balanced. So this force, how much will it be, guys? K, Q with negative Q, QQ divided by, oh, I don't know that distance, so let's call that distance as x. Let's call that distance as x. So KQQ divided by whatever that distance x square is. Is that clear? Everyone? Pakka? Understood? So this and this will face attractive, and the attractive force will be KQQ divided by this distance square. Oh, got it, sir. So one last thing before we go ahead. Remember, this entire distance was L. So how much should this be? Just like we said, this is x, this is x. So this will be L minus x. And same way, this force can be given by K, this charge with this charge, Q, 4Q divided by distance square, which means L minus x whole square. So I want this entire system to be in equilibrium. That means these two should be equal, or these two should be equal. So if I equate these two, I think we can start looking at the numbers and get the answers. So first of all, let's equate these two. So it will become K, Q square multiplied by 4 divided by L square will be equal to this, which is K, QQ divided by x square. Q cancels, K cancels. So what am I left with? Observe carefully. 4 times of Q divided by L square is equal to this capital Q remains, K has gone, and this x square is remaining. That's all is left. From this, capital Q is 4Q x square divided by L square. 4Q x square divided by L square is nothing but capital Q. Now look at these two forces on this 4Q charge. They too also should be equal to each other. Only then it will be in equilibrium. So I will say K Q into 4Q divided by L minus x the whole square will be equal to, what is there on the right hand side? It is K 4, or rather K Q square multiplied by 4. Is that right? Yes. Divided by L square. Wait a minute. Q I already know. So I'm just not going to waste time. I'm just going to put it over here. So if I put it over here, it will become 4Q x square divided by L square. Rest of the terms as it is. K is there as it is. 4Q small is there as it is. And of course, L minus x whole square is also there as it is. On this side, what do we have? We have 4KQ square divided by L square. Now let's try and cancel as many things as possible. Like I can see this K and this K going. this 4 and this 4 going, this L square and this L square going, Q with Q goes with Q square, perfect. And anything else, guys? No, right? So what am I left with? Let's just check. This 4 is remaining. So 4x square is there. Take it on the other side, L minus x whole square. So L minus x the whole square. Great. Take square roots on both sides. So 2x will be L minus x. 2x will be L minus x. Shift x on the other side. So it will become 3x is equal to L. Therefore, x is equal to L divided by 3. So L divided by 3 is option A. That was such a brilliant question which was asked in JEE Mains 2019. Got it? How many of you loved this question? How many of you loved this question? Edits, very good. L by 2 is not the right answer. No, it's not L by 2. Okay, very good, very good, very good. Excellent. Okay. Amazing, amazing, amazing. Very nice, very good. Hey guys, who is this spamming? Vanakam. Hey, waste fellow, go man. Why have you come here? Go to that place only, wherever you have come from. Because that is the kind of manners your sir has taught, 100%. That's why you have come here. So, let's go ahead to the next question, guys. Now, yeah. This is also, I think, one previous year question, but this is easy only. There is a regular hexagon, and on the vertices of that regular hexagon, you have placed some charges, Q, okay, then 2Q, then over here, then minus Q, and then the side length is A. What happens is, you take another charge at the center, and the question is, find the force on capital Q. That's the question. Simple question. What is the force on the charge capital Q, which is exactly at the center of a regular hexagon of side A? Okay. Alright. Shall we do this? Alright. Very laddu question only. Now, this kind of question always, most of the times, will involve some kind of symmetry. Like for example, over here, this 2Q on this Q will apply a force like this. This 2Q on this capital Q will apply a same identical force in the opposite direction. Can you see both these forces are equal opposite? So they end up cancelling. Same way, this negative charge on this Q will apply an attractive force here. This negative 3Q will apply an attractive force here. Equal distance, equal charges again gets cancelled. So most of the charges literally are cancelling out. Now the only things which will matter is this. A lot of people think Q and negative Q will also cancel. Think again, yeah. Q on this Q will repel this Q, so it will be a force like this, correct? This negative Q on this Q will also apply a force of the same magnitude, but attractive force, so it is exactly in this direction, not in the opposite direction. Obviously, repelling charges this way, attracting charges this way only. So, these both forces are going to be equal, and each of this force, how much will it be? K into charge 1, which is Q, into charge 2, which is capital Q, and what's this distance going to be? Well. Inside a hexagon, you get beautiful triangles, isn't it? 6 congruent equilateral triangles like this. So all the sides are basically A only. Everything is A. Everything over here is A only. So the distance between them is not anything else. It's just A only. That's the force. But there are two forces like this. So the net force will be 2 times K Q Q divided by A square. That's it. K Q Q divided by A square. Simple? Very good. Alright. Oh, my 2026 students lecture helped me a lot. JEE preparation also for my NEET. Thank you so much. I'm so glad, Dr. Takshin. I hope you get your dream college this year only. But if not, I'm always there even for all the students who are trying to repeat. Okay? Great. So, to summarize, till now, whatever we have studied, Coulomb's force is an inverse square law force similar to gravity, whose value is the product of the charges and inversely related to the square of the distance. That K is the Coulomb constant, which depends on the medium. Specifically for vacuum and air, permittivity value is 8.85 10 to the power negative 12, and Coulomb constant is 9 10 to the power 9 in SI units. If you change the SI units, if you change the units from SI to CGS or FPS or something, obviously K and epsilon will change because they are dependent on Coulomb, Newton, meter and all of that. Okay, so these depend on the units also. You will also see one interesting thing, which is the electric force by gravitational force is always a constant value. Now, before going to that, let me complete this 7th point. Superposition principle is based on a property which says that two charges will attract or repel each other irrespective of the third charge. See, a lot of people take superposition principle very lightly. What is there? Sir, there was a charge here and there is another charge here. Fair enough. So, if there was some force between them, then even if you put another charge, let's say Q2, yes sir, there will be a new force which will come and then there will be a net force. It feels very natural, but in physics there are some forces you will learn at higher MSc level or BSc level or engineering physics level, that it is not always true that this principle is applicable. So electric forces, yes, but nuclear forces and all that, it's crazy. So what happens is, if another charge comes, then the value of F1 only will change. These two will apply force between them, that's a different story. I am saying the mere presence of an other charge will affect the force between the original two charges. That's scary and crazy also. So luckily, electric magnetic forces do not behave that way. It's like, you two are very good friends, but the moment teacher comes, we should not talk, shh, don't talk. Or some secret relationship is going on in your school, in your batch. Have you seen that secret relationships? Nicely, boy and girl, fully boyfriend, girlfriend only, but in front of everyone, when nobody is watching, that is what is different. So, if they behave differently, then it is not following superposition principle. Somebody is there, not there, doesn't matter. These two attract, they will attract. So, that boyfriend, girlfriend is there, teacher is there, friends are there, nobody is there, anybody is there, I am anywhere, always in that same situation. Got it? That is your superpositioning principle. Is this clear? Understood? Clearo? Perfecto? Amazing. What about this? This says gravitational force by electric force or electric force by gravitational force. So if you divide electric force by gravitational force between two charges or two masses, electric force is Coulomb constant Q1 Q2 divided by R square. Gravitational force is G M1 M2 divided by R square. R square goes. So you will be left with K Q Q divided by G M1 M2. Now if you take regular proton electron, masses are defined, distance does not matter, charges K and G value also if you find that value, that comes out of the order of, this is very important value, remember this number, 10 to the power 39. This has directly been asked in JEE mains and sometimes in BitSet and so many other places. The value, directly from NCERT they have taken this. So huge, which tells that electric force is much larger than gravitational force. Between same two particles, same two masses, electric force much stronger. Got it? So that's why you will see in the natural forces, elementary fundamental forces of nature, gravity is the weakest force, then is your electric magnetic force, then is your nuclear forces. Nuclear forces are even stronger than electric forces. Understanding it? Is that clear? Everyone? Pakka? Clear ho? Understood ho? Very good, very good, very good. So all these things are there in your summary pointers. Now it's time to go to electric field. Shall we go to electric field, guys? Okay, ready for it, ready for it, ready for it. Or shall we take a small break? We'll take a small break and return. Okay, we'll take a 10 minutes small break and then we will start with this. Okay, so I'm just going to give you 10 minutes break. Let's come back. Oh, thank you so much guys for pointing it out. So I am back. It's time to continue with the next concept of electric field. Before this, we talked about charges, their properties, Coulomb's force and superposition. Now let's see electric field. Electric field was introduced in 11th standard in the chapter of gravity. You might have forgotten, that's okay. So we'll revisit this. But this word field sounds very familiar. Okay, this word field sounds very familiar. Imagine there is one big person, healthy person, bodybuilder. Anybody is very angry bodybuilder. Anybody comes in front of him, dishum. He sees. If the person is there over there, that's it, dishum. Doesn't care who it is, what it is. If one big person comes, he gets even more angry. More force, dishum. So think of this person like a charge. He sees another charge which is small. He applies a force, dishum. If that charge is bigger, even bigger force, more dishum. Understanding this concept? This bodybuilder person is a charge. He sees another small person, small charge, dishum. Bigger charge, bigger person, more dishum. Even bigger person, more dishum. That's what this person does. That mental fellow. Doesn't matter. Now that person is just sitting quietly. Nobody is there around. Because if anybody comes around, dishum, 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 force. Force 1, force 2, force 3, force 5. He will start applying. Correct? Now he is solo sitting. Somebody will come. If you come, dishum. If you come, dishum. So what he is making around is a terror. His terror is felt. Everybody is scared to go near him. Everybody knows his aura. His presence is creating a fear in that vicinity, in that area. Now, some new fellow comes from some distant place. He is like, why is everybody so far away? What is happening? Then everybody tells, hey fellow, don't go close. You will get hit. Then this person is like, oh, is it? Let me check. Let me check. So that person, another new person comes slowly. And he sees, he experiences one push, dishum force on him. He gets tested. Oh yeah, what these people told is right only. So, this aura, this presence which is being felt is exactly called as the field of that charge. That bodybuilder was the source of the field around him. And that field is looking out for charges to apply force. Without another charge, that field is just a mere presence, a terror which is being felt. That, hey, listen, if you come here, I will apply this force. If you come here, I'll apply this force. So, the field is basically a kind of an information which is there around a charge which sources that field. If an actual charge comes, that field applies a force and the presence is being made felt by applying that force. So, read this now. You will understand it. If a charge small q is left, then what is left in the surrounding is removed, then what is left in the surrounding? There is a charge, capital Q, another charge, small q. Now, if small q goes, capital Q remains, what is left in the surrounding? Nothing. If there is nothing, then how does a force act if you place that charge back? So, I am this blue charge, this small q is being removed, then there is nothing. If there is literally nothing, then how is it that when you place this charge back, it knows how much force to experience? So, if it knows, if I am here, this much charge I have to experience, that means before even placing the charge, there was something present. And that something present is the concept of field. According to this, we say that charge Q, I am that charge Q, I am producing an electric field everywhere around me, around the surroundings. Is this concept clear? What is the meaning of electric field, my dear warriors? Pakka? Dishum. Ayo, dishum means as a punch. Ayo, what man? You don't watch movies, huh? Thalapati movies. No movies you guys watch, huh? Durandar, any movie. Dishum, dishum. Dishum, dishum. What I have to explain now? What is dishum, dishum? Ayyo. Okay. Anyways, coming back. Now imagine there is a dawn, there is a charge, there is a system of charges. Anything, doesn't matter. Positive, negative, 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 positive, doesn't matter. It's a charged body. This is our source of field, which is basically a charged body. I want to know what is the field at this particular point. So what I will do, at this point, I will bring a charge to test. I need a charge, because how else will I test whether there is some field around it? Correct? You cannot say, there is field, I know it, it is there. Arey Baba, how do you know? So that you need to test it. Like we take a blood test to see whether you are B positive, B negative, this positive, that negative, correct? So you need to test. But while testing, do you suck out the entire blood? Shreyas Sir went to do blood test. Whether is B, O, whatever, AB negative testing. That nurse came, full blood she took, one bucket full of blood. Sir, you are B positive, B negative, whatever. Ayo, that person only gone. For testing, you will take one small sample, no? Same way, to test whether there is field, you will take a very small charge. Why? If this charge is big, then this guy will start pushing these charges here and there. This body only will change. So you cannot do that. You cannot disturb the original system. It has to be as it is. So you take a small test charge. Small test charge. But sir, I have one more issue. If you take a positive charge, then the direction will be different. If you take a negative charge, then the direction will be different. Very smart. Correct. If I take positive, if I take negative, the answers will be opposite. So we'll remove that ambiguity. Let's create a standard. We'll always take positive value. So small positive test charge. Because then, whether you are in America, whether you are in Africa, whether you are in India, or whether you are in Antarctica, everybody for testing will always use the same thing. Or else one person will use different things. Then how can it be standardized? Correct? Will not arrive at the same conclusion. So to arrive at the same conclusion, we'll always standardize the test charge as a positive test charge. Now I find that because of these charges, this test is experiencing some kind of force. What I will do, I will take that particular force and divide it by the test charge. What will remain is called as the electric field. Will be electric field. Whatever is the force direction, it's the same direction as that of the force. Force divided by the charge is that electric field. The symbol of that is E. It's a vector quantity. Because force is a vector. Force direction and field direction are always going to be the same. Okay, test charge is always positive. Now, having said that, look at the units. Force is in Newton, charge is in Coulomb. So the SI unit, needless to say, will be Newton per Coulomb. Later on, you will see a new unit which is volt per meter. That will come later. Right now, don't worry about it at all. Okay. So how do I define electric field, sir? electric field vector is then whatever force that charge will experience, that small positive charge, I'll call it Q. So Q over here, but it has to be small. How do I show small? I will put limits. So I'll put limit Q tends to 0. So this is the value of the electric field due to any force which is experienced by a small positive charge. Is this clear? Is this clear, everyone? Pakka? Awesome, awesome, awesome. Right now there is no droppers batch or Prayas batch in pure English. Yes, Hindi batches are there, or Lakshya for 12th and Arjuna for 11th is there. So maybe by next year we'll have enough number of students. This channel is also new, plus I came right now, right? Just 1 month back. So 2 months back, barely, what, 1st May or something I came to this channel. So guys, give it some time. So we need decent number of students because we have to dedicate a lot of resources for running a batch. It takes a lot of effort, energy, people, money, lot of things it's going to take. So give us some time. Okay. Last 5 years is decent enough for 99 percentile, but that alone will not be enough. It is must, but not enough. Great. So that is what has been put over here also. Same thing. So E is limit Q tends to 0, force by Q. So that source charge will be creating that field and will apply the force on this small positive test charge. Same thing has been mentioned. Now, how much is the value of this field if my source charge was a point charge? Let's say it is a point charge, capital Q, and now I am at some distance r from it, and at this particular point I want to know what's the field. So first I'm going to bring my test positive charge. This is my test positive charge. This is the source charge. This is the source which is going to create a field around it. So for testing that field, I brought this test. So on that test, there will be a force, of course. And if there is a force, there will be also a field like this. And that field, I will call it as E. So let's find out the magnitude of the field. It's very simple. I just have to write the limit definition. Limit Q tends to 0 divided by Q. And then there is this particular force. All right. So first of all, what is this value of the force? It is nothing but 1 by 4 pi epsilon naught capital Q small q divided by r square. Is that right? That is the value of the force. Great. So I'll put a limit Q tends to 0, and this whole thing is also divided by Q again. Yeah, because this Q is there, same Q is there over here also, and this was just the definition of the force, Coulomb's law. Guess what happens? This Q and this Q cancels. Now in this expression, there is nothing which involves small q. So there is this basic rule of limits. So limit x tends to 0, if x is there, yes, the answer is 0, but limit some other variable is there, a, and x tends to 0, doesn't matter, it is going to be a only. So same way, this is some other variable, but I am taking the limit of some other variable itself. Okay. So there is nothing to take limit of, hence I am just left with, what am I left with? Just this entire number, which is 1 by 4 pi epsilon naught, q is there and r square is there. That is the magnitude of the electric field. This is electric field due to a point charge. Electric field due to a point charge. Who is our point charge in this case? Our point charge is capital Q. Due to that charge, how much field will be there? Because there is 1 by r square over here, if I draw a graph of how that field will vary with distance, it will be like this. It will be a curve. It is basically inversely related to r square. Electric field is inversely related to r square. So that is why that graph will be like this, 1 by r square related. Clear? Very simple. Okay, the same thing has been put over here. This is in vector form, just one unit vector. If you put it is a vector form, but magnitude wise 1 by 4 pi epsilon naught q by r square is the electric field due to a charge. Due to a charge. There is no QQ. Force will have QQ. Field will only have Q in the numerator. That's one big simple way of remembering the formula. Alright, sir. Got it. Everyone till this point has understood. Then I will tell you about a question. Say for example, what is the field at distance of 3 nanometer from a proton? That's the question. Let's have a look at it. What's the field at a distance of 3 nanometer from a proton? Proton is a positive charge. 3 nanometers is that distance. That means 3 into 10 to the power minus 9 meters. And at this point, I want to know what is the field. What is the field? Because we are talking about a proton, the charge on it is positive 1.6 into 10 to the power minus 19 Coulomb. So, using the formula of the electric field, 1 by 4 pi epsilon naught Q divided by R square. This is 9 into 10 to the power 9. My charge is 1.6 10 to the power negative 19 Coulomb. The distance is 3 nano. Nano is 10 to the power minus 9, but I have to square it. Let's see what happens. 9 is there. 1.6 I can write it as 16. This is positive 9. This will become minus 20 because I've shifted the decimal in 1.6. 3 square is 9 and minus 9 square is minus 18 of course. 9 cancels, only the number 16 remains. Okay, so minus 18 minus 20. Minus 2 will remain on the top. Minus 2 and plus 9 will make it plus 7. So 10 to the power 7. That's a huge value. So basically 1.6 into 10 to the power 8 newtons per coulomb is the value of the electric field. 1.6 10 to the power 8 newton per coulomb is the value of the electric field. Very simple and straightforward. Correct? Pakka? Awesome. I'm so glad Dhuraj Sharma, IIT Bombay, and this channel is meant for all the kids who want to learn in English but not very sophisticated Shakespeare ICSE type of English. I talk very normal English, though I can speak very good level of English. I try to keep it very normal. Okay, I want to make grammatical mistakes because that's how you talk. I don't want to sound very perfect. I don't want to. Okay, this is not an English class also. This is a physics class, but unfortunately, so many videos and good teachers are teaching in Hindi. And I have seen this again and again. Many people tried to create an English channel, but miserably failed. And I'm so glad that I am here and making sure that this channel reaches maximum number of students and it becomes successful. Yeah. So thank you for all the love. All right. Now let's go to the next concept. After learning about what is the electric field due to a point charge and how to calculate it, the next point is the electric field. How does it look direction wise? It's very simple. See, if the source charge is positive, then if you place a unit positive charge for testing, positive and positive will always repel. So the force on it will be always repulsive. They will always repel, and hence the field naturally will have to be in the outward direction. So the field will be repulsive in nature, so it will be away from the positive charge. But if you take a negative charge and you place the same unit positive charge or test positive charge, then they will obviously end up attracting. they will obviously end up attracting each other. If it attracts, what will happen to the field? The field will be inwards or towards the source charge. So that's why you will see radially inward field because of a negative charge. So positive charge gives outward field, negative charge will suck the field towards itself. Source positive, sink negative. Sink means it goes inside, source means it comes out, like the rays of the sun is a source. Sink is which absorbs. So sometimes positive is called as the source of the field and negative is called as the sink of the electric field. Okay. Also one more thing to note, that if I am at the same distance from the positive or from the negative charge, at all these points, at all these points, because the distances are same, the magnitude of the field will also be the same. It's not that here it is more, here it is less, more. No, same field. Even at all these points, same field. But yes, this point and this point, distances are different. So the field will be different. So as you change the distance, you will see the field will be different magnitude wise. But at the same distance, no matter which direction you go in 3D space, it's like a sphere if you think about it. So on that sphere, the magnitude of the field will be the same. Okay. So these are the basic things which have been mentioned. So at equal distances, the magnitude is the same. All right. So it's basically the same on a sphere. That's all. And this is for the positive charge and one for the negative charge. Directed radially outwards for a positive charge, and if the source charge is negative, then it points radially inwards. All these are there in your textbook, which is basically NCERT. Great. Now let's look at the reverse. Meaning, there is something which is creating a field. I don't care what it is. Something is there which is creating some kind of a field. And that field might be like this. The field is something like this. This is our electric field due to something, and now I happen to place an actual charge, not necessarily positive or negative, it could be anything. If I place a real charge over here, you will see that it will always, wherever I place it, let's say I place it here, it will always experience a force in a direction which is tangent to the field. So this is the tangential line. I'm just trying to make it as perfect as possible. This is nothing but tangent to the field. Tangent to the field. Along the tangent, this will experience a force. And how much force will it experience? It's very simple, because by the definition, field is force by charge. If I take charge on this side, force will be equal to field multiplied by the charge. Field multiplied by the charge. So exactly what we would get over here. The force will be nothing but whatever charge you place multiplied by the electric field. That's it. That is the formula. That is the formula. And this force will be always along the tangent. Now it so happens that if my charge is positive, then you will see that the force vector and the field vector are in the same direction as the field. And if the charge happens to be a negative one, then whatever is the field, it will be opposite. The force is opposite is opposite to the field, opposite to the field, not as the field, is opposite to the field, opposite to the field. Meaning if you take the charge over here, the field is in this direction only. But if this charge is positive, then you will see force is in the same direction. But if this charge is negative, then the force is in the opposite direction, because negative means it will multiply the vector with a negative number. So the force becomes opposite in nature. So for positive charges, this is positive, it is in the same direction, but for negative charges, it's in the opposite direction. So always remember the force is along that tangent. Okay. So this formula is very important. It is there same way in your NCERT too. The electric force on a charge can be looked up as an interaction, and if we denote the position of the charge by some vector, okay, so there is a charge, it's located here. At that point, there is some field at that point, R is that point. Then the field at that point into the value of the charge will give me the force on that charge. So that is what they have mentioned, but this I have given you additional information how the direction will change. Positive is same, negative is opposite. Simple as that, nothing great. So just to give you an example of this, just imagine there is a charge of 2 microcoulomb and mass 10 milligram moving in a field of 20 volts per meter. Find its acceleration. Find its acceleration. That is the question. Let's understand. So we have a charge. It is going in some electric field, and because it is going in an electric field, it will experience a force. And because it experiences force, it has some acceleration. The question is to find out this acceleration. So logic says first figure out how much the force will be. Force will be the charge multiplied by the field. Also, by Newton's law, force is mass into acceleration. That means m into a, force is the same, is q into e. Therefore, acceleration will be charge into field divided by the mass. Charge into field divided by the mass. Perfect. This is what I was looking for. So I know the charge. It's 2 microcoulomb. So 2 into 10 to the power negative 6. Field is 20. Volts per meter is a SI unit. So keep it as it is. Mass, milligram. Milli is 10 to the power minus 3, but gram is a CGS unit, converted into MKS, SI units. So it will become 10 to the power minus 3 into minus 3 minus 6. So 10 into 10 to the power minus 6 kilos, always kilos for SI unit. Many people keep it as minus 3, which is wrong. Okay, so A will be equal to 2 2s are 4, and minus 6 and 1 0 will make it minus 5, of course. And this will also be minus 5, minus 6 and 1 0. So this is basically 4 meters per second square. Very good. Amazing. Now what might happen is, okay, we got this answer. Many times you might probably get a diagram like this, where it is told, listen, there is a kind of an electric field like this. Electric field like this. And this field, same value I will take, 10 volt per meter, and charge also I will take same only, but I will take negative, let's say. I take negative, let's say. minus 2 microcoulomb, and then it has been thrown like this, okay, with some speed, God knows, maybe 10 meters per second, and maybe at an angle of 60 degrees to the field, like this. And that field is originating from some plate, electric plate, which is there. Question is, when will that charge strike back that plate, assuming the mass is still, what is that, 10 milligram. 10 milligram. When will the charge strike back the plate? That's the question. Now you might think, what the hell is this question? How do I do it? It's not a crazy question. It's very simple. See, it's a negative charge. Negative charge means force will be opposite to the field. 100%. Field is here. Force will have to be opposite. So the force naturally will be in this direction because it is negative charge. Now whatever is the direction of the force will be also the direction of the acceleration. So acceleration will also be like this. Now forget there is field, forget there is charge. Just treat it like a simple problem. There is a mass, there is acceleration, there is a line. Oh, this looks to me like a projectile motion. This acceleration looks like acceleration due to gravity. This is velocity of projection, and this is now projectile motion. And projectile motion means it will go like this and it will hit back over here. Charge will strike back the plate after how much time? Oh, this is basically time of flight. Time of flight. That is what has been asked. And what is the formula for time of flight? Time of flight is 2u sine theta divided by g, isn't it? But don't rush and put g as 10. Here, this g is basically a. This g is basically a. Acceleration due to gravity replaced by just pure acceleration. And this value, we just figured it out in this question. Same values were there. We solved the same values, mass, charge, everything was same. We figured it out, it was 4 meters per second square. So this is going to be just 4 meters per second square from our previous question. Oh, so that's it. Oh, what is the speed? It is nothing but 10. And sine of 60 degrees. Great. What is the value of g? It is 4. So 2 into 10 multiplied by sine 60 is root 3 by 2 and 4. 2 cancels, 10 by 4 is 5. So 5 root 3 by 2 seconds is the time. That's it. If you want to find range, height, everything, kinematic equations, everything can be applied like your regular two-dimensional problem. Can you see that? I'm currently in the Lux batch. I can watch this. Definitely, you can watch this class. It will help you for your backlog. 100%. Please watch it. Okay. But yeah, better will be to also watch your recorded classes of the same teacher from your Lux batch in NEET. So that will be also better. Alright. Very nice. Great, sir. I understood how this formula has to be used. Force is charge multiplied by field. So either directly to find forces, acceleration, or sometimes combine it with projectile motion as well. Okay, now that we have learnt about this, the next concept is field due to multiple charges. It's the same like force due to multiple charges only. So here what will happen? You will have a charge from different directions, different fields will come. So this point, there is no charge, remember that. This point will experience or will have fields in different directions. So the net field at that point will be simply the vector sum due to all of them. And that is again by superpositioning principle. The net electric field is given by this. And remember, this is a vector addition. Vector addition. Actually, this is bold. So bold alphabets means vectors, but it is not seen over here. So I'll put bar to explicitly mention that, remember, this is always a vector equation. Okay. Net electric field is the vector sum of individual field contributions from all the charges. All right. So let's do some questions, but before that, imagine there were charges like this. One is Q, one is, let's say, another Q over here, and let's say there is minus 2Q over here. And we have been asked to figure out exactly at the midpoint, find the field, find the net field at that particular midpoint on this side. This is an equilateral triangle. All the sides are A only. Okay, this is this particular point. You have to find midpoint actually. This is midpoint. What is the field at this particular midpoint? Let's solve this question. Okay, there are multiple charges. Each charge will have its own contribution, and all the vector sum will give me the net field contribution. But luckily or funnily, these two charges are same and also at the same distance. So what happens is, at that particular point, you will notice this charge at this point will give an outward field like this. This charge at this point will give a repelling field like this. They are positive. And this field due to Q and this field due to Q are equal and opposite, so they end up cancelling. So EQ is equal and opposite because charges are same, distances are same. So that means they end up cancelling, and that means they have no net contribution. They have no net contribution in the net electric field. So let's forget these two because they anyways are cancelling out. So the only field remains due to negative 2Q charge. But the distance is not so simple. It's this distance. Okay. That we can calculate by simple trigonometry now. So we can see this is 90 degrees. Obviously this is 60 degrees. So this height h which is there, that will be A sine 60. Sine 60 is opposite by hypotenuse. Sine 60 is root 3 divided by 2. Now this is a negative charge, so negative charge will always give an attractive field. So the attractive field will be like this. So this is the field due to negative 2Q charge. What's the magnitude of that? That will be Coulomb constant into the magnitude of the charge divided by distance square, that means h square. So K multiplied by 2Q divided by h, which is A root 3 by 2 whole square. 2 square goes on the top, multiplies with this 2, it will become K multiplied by 4 multiplied by Q divided by A square multiplied by root 3 square is 3. That is the force due to minus 2Q, but that will also be the net force. Net force is only due to this, so the net force is exactly this value. Yeah, simply write it 4KQ divided by 3A square. That's the answer, 4KQ by 3A square. Got it? That's how you can apply superpositioning principle. Yes, midpoint, no. Midpoint of a side field is not 0. Mid of the triangle, which is a centroid, the field will be 0. That too if all charges are equal. In this situation, charges are not even equal, bro. So they will not even cancel. So don't buy it like this. Midpoint field is 0. No. See the symmetry. This and this will cancel. But this, who is there to balance it? Nobody. So there is an unbalanced field. And that's why field is not 0. Is that okay, Bhavish? Yep. Now guys, one simple thing. This series will only run due to one and only one thing, your support. More people watch, okay, live if you watch even better. I would want you to watch it live, but fine. Due to some reasons you are not able to watch it live, please watch it. And I check everything. Who is watching, from which state, which city. I want full support. I keep a track of everything. Okay. I will see all the comments. I will see how you are engaging in that lecture. And if you show that support, trust me, you will see all the lectures. I don't want 100, 200 people. I want thousands of people watching it, because it takes a lot of effort, guys, and I will demand it also, and I have full right to demand it, because I have that experience of teaching. I have been teaching thousands of students, 14 plus years. I have myself done my IIT qualification, did my research from IIT Bombay, got so many selections of students. So I feel I should demand from all of you that you guys need to support, because such quality teachers, I am not praising myself, but really guys, I am doing a lot of it for you. Okay, that too in pure English. Nobody is going to do this. It was the effort of us which is bringing you this particular lecture over here. Okay, so I know what you guys need. I know what you guys want. So if you want me to do that, please support. Okay, tell about this channel, tell about this video, tell about Shreyas Sir, tell about the team, and tell them, listen, you are serious, right? Don't tell to unserious students. Somebody is not serious, don't tell. No use. Serious students should know about what we are doing here. Simple. Because rank will only come from seriousness. Rank will only come from experience. Rank will only come from dedicated, full-fledged, proper classes, quality content. Otherwise, one shot, I can teach this chapter in 1.5 hours. Easily. But I am not doing that. You can see how nicely I am going through this particular chapter. Alright, let's go. Next question. A particle of mass, charged, released, field, kinetic energy attained after some distance. 2020 question. Let's see how many of you can do this. The polls have started right now. Think, how are you going to do it? Kinetic energy is asked. Field is given. Charge is given. Mass is given. For kinetic energy, I need speed. Mass is given means speed is needed. For speed, how do I find speed in that field? Field will apply some force. Force will cause some acceleration. Acceleration will give the speed. Oh, so kinematics. That's the logic should develop in your mind automatically. Thank you. Thank you so much for all the support, guys. Alright, so let's see. First, let's calculate the force. Will be charge multiplied by field. Now, by using Newton's laws of motion, I can say that same force is mass into acceleration. Now, equating these two, because you can see the same force will cause that acceleration. So, Q into E is M into A. Therefore, acceleration is QE divided by M. Alright. Sir, now what to do? Use kinematic equation. Now, if you use kinematic equation, V is U plus A into T. It starts from rest, so 0. Acceleration QE divided by M. And, oh, distance, not time. So I can't use this. So I have to use something else. Now, V square is U square plus 2as. Okay. So V square is initial speed is 0. Acceleration is QE by M and distance is S. So from this I get V square is equal to 2QE S divided by M. I'll keep it as V square because I need V square only. Kinetic energy is half M V square. So half M is there. V square is this. So 2QE S divided by M. MM cancels. So it will become 2QE S. But 2 also get cancelled. So 2 also gets cancelled. That means only QE into S. QES is there as option A. Mark it and go ahead. And let's see whether it is right. Just, where is this? Full stop. Show results. Very good. 100%. Ayo, what are others doing? Use the Pylons app. Use the Pylons app. Yes, Bhargav. I can't be in quantum state. No, I can't be at two places at once. Heisenberg uncertainty or like that Heisenberg cat. I am there at two places in quantum state. Shreyas Sir is in this also, that also. Some people are asking, sir, you are in that organization also, kya? Oh, yo, bro, I left that how many years? 5 years, 4 years. You still, where were you all these years? I am here now. But I feel this is a lengthy method. Hai na? Such a lengthy method, guys. Yo, what is this? Field, force, Newton law, kinematics, kinetic energy. My God. Instead, I think of a better alternative. And I will tell, work kinetic energy theorem says work is change in kinetic energy. Work is change in kinetic energy. Final kinetic energy is K, initial is 0. What is work? Force into displacement. So this is K. What is the force? Charge into the field. So QE into S is K. That's it. In 3 steps I will get the answer. This is using work kinetic energy theorem. Work kinetic energy theorem. So that is why you should be very, very alert. You should have all your basics, alternatives, multiple methods in your head. Or else, if you don't have that enough practice, you will be doing like this. So much time got wasted. But this method, 3 steps. Tuck, done, dusted, go ahead. Schrödinger. Oh, I told about Heisenberg cat. Sorry, Schrödinger cat. My bad. Thank you so much. Yeah, I do speak Hindi, man. I'm also there on the Maharashtra channel, MST CET channel. Right? There, I talk in proper Hindi only. Okay? Alright. Great. So, moving on to the next question on your screen. Electron, proton separated, allowed to fall through same distance h in vertical field, reversing field direction appropriately, ignoring gravity, the time of fall for the electron and proton. Ayo, see, what is this? It's nothing, simple. There is one line here, one line here. One second. You take a proton first. Proton is a positive charge. Proton is thrown in positive field. Proton is thrown in some field. So it will experience some force, and that force, acceleration, everything will be in the same direction only. Force, acceleration will be in the same direction. Next time you are taking a negative charge, that also has to fall down, but then for the force to be like this and acceleration to be like this, because it is a negative charge, we need to ensure the field is opposite in direction. That's what they have mentioned also. Take appropriate reversing fields, take appropriate field direction, ignore gravity, that's it. So who will reach faster or slower? In either case, whatever you see, acceleration is force by mass. Force is charge into field divided by mass. Notice, charge magnitude wise is same. Whether it is plus or minus E, it is the same thing, magnitude. Field is same. But mass of a proton obviously much larger than mass of an electron. So if the mass is more for a proton, acceleration is less. So acceleration of a proton, heavier particle, it will be less as compared to acceleration of an electron. So for the same distance to be covered, I think drop through same vertical distance, height is same, acceleration is less, obviously slow acceleration, time taken will be more. So time taken by the proton will be more than the time taken by the electron. So time taken by the electron will be less. So option C for Captain Shreyas. How many of you wrote C? Very good. Very good. Yes, Silis, RV, what should I reply to you? How many years of papers to refer? See, it's not about how many years. I would say it is about the quality of the questions. a lot of people say just do last 5 years. But what will happen if you take any year, let's say 2023, in a particular year, the type models of question will be similar. In all the shifts, you will see a lot of similarities are there. So it's not good enough practice. Fine, you practice 2-3 shifts here and there, good. After that, go to some other year. So practice some 2-3 shifts from each year, from attempt 1, April and January, and then go to some next year. But before 2020, the number of attempts were less, and before that even less. So, you might see fewer questions, between 2010 and 2020, right? But the quality of questions are very good in that era. So those quality questions you should solve. And that won't take much time, because if you solve, let's say 2013 paper or 2015 paper, not much time, because there is only one set. That's it. So distribute it, spread it, and go to old papers which has quality questions, because those question models get repeated again and again, somewhere or the other. Okay? Yes, the mass of a proton is quite large, close to 1800 times the mass of an electron. Now, what is the physical significance of electric field? There is one beautiful paragraph which is given over here in your NCERT. Although, these kind of paragraphs are unnecessary, which add to inferiority complex of the students. And sometimes I feel the authors want to show off a little bit. Listen, this, like these kids are there, in school. Ma'am, where will you use integration, ma'am? Ma'am will be like, in the future, one day, when you will be an engineer, that day you will be using integration like this. Then the kid becomes very happy. Then after 10 years, kid has joined the job. And then he looks around, where am I using integration, bro? You are not using integration. Then he asks his boss, where do I use integration? Boss will be like, hey, what has happened to you? Shut up, use this Excel sheet, enough. Done and dusted. Use presentation, Excel sheet, 2 things, and email. Job is done. Then the kid thinks, my whole life was a lie. Why did I learn integration? So, very similar thing, this NCERT fellow has tried to show off. Listen bro, electric field, lot of significance in the future, you will see this is how it is, like that and all. But yeah, for physics enthusiasts, it's quite interesting. And talking about the point, sir, won't integration be useful at all? Then why am I learning? See, it's never even think about whatever I'm learning, how will I be using it in day-to-day life. 99.9% of the things that you learn will not be useful at all. I mean, you have learned about history, geography, civics, physics, English, authors, this, that, languages. Do you really think whatever you are going to do for the rest of your life till the age of 60, 70, 80, 90, 100, do you think you will be using all of it? Obviously no, bro. But then what is the use of it? It is necessary because the time you spend learning it, the art of learning that integration is very important, because that skill not only helps you in learning that integration or learning about whatever concepts you are trying to grasp, but that skill helps you solve real life problems. Because why on earth would an IITian be picked for a finance company? Because they know, these people know how to think better. Their analytical minds are really good. Their mathematical minds are really good. It's not that they are going to use the exact same concept, but that skill which you develop, the art of learning which you develop is what is useful. And that is what is more important than the real integration. Is that right? Yeah. Keep that in mind. Anyways, so talking about this, what is the physical significance of, the electric field, and they have tried to tell you about how, electric field produces electric charge produces a field around it, and it is independent of the test charge, and This refers to a quantity which is defined at every point in space and may vary from point to point. Field is a vector. Okay, fine. In true physical significance, however, emerges when we go beyond electrostatics and deal with time-dependent electromagnetic phenomena. Suppose we consider the force and accelerated motion. Now the greatest speed to which the signal information can go is c, and thus the effect of motion cannot arise instantaneously and there will be some time delay. And precisely here the notion of electric field, the electromagnetic field is natural and very useful, blah blah blah. Okay, I'll tell you in simple words what this means. Okay, first of all, if you have some charge, then the field over here which you get, does it depend on the test charge? No, right? Whatever the test charge is doesn't matter, because we saw when you try to find the field, look at this derivation. This is very important derivation which we just did some time back. Here, when you try to find the field, this q, which is a test, doesn't matter because anyways it gets cancelled. It happens always. The test charge gets cancelled, so it's never dependent on that test charge itself. It depends on the source charge who is creating that field. That's the first paragraph essentially. And it's a vector quantity and all of that, that is understood, okay. But what is also important is, imagine there is a charge over here, okay, and then there is actual another charge over here. They are experiencing some kind of force. Now imagine this charge is suddenly moved here or here or here. So the distance changes, force has to change. Now a lot of people think the moment I move this charge, immediately the force will change. This notion of immediate is wrong, because this charge has to tell this charge, bro, I am here, bro, I am here, I am here, I am there. That information flow itself takes some time. And field travels at the speed of light. Nothing, literally anything, nothing can travel more than the speed of light, not even information. Actually, the speed of light is not just the limit of the motion of particles, but it's also the limit of the speed of the information. You can't transmit the information faster than how much light can move. So, this information that this charge has moved can't reach this guy until light arrives. Basically, you can't travel faster than that. So, when this charge moves here, what will happen? That field will take some time to reach here. After that, the force will change. Yes, the time delay will be small, but it is there. And if the distances are huge, speeds are huge, then that makes a huge difference. So, it is not instantaneous, it takes some time. And this is not just true about this, but also about gravity. Like for example, if today the sun were to disappear, don't think, sir, sun is gone, the earth will fly off. Wrong. It will take 8 minutes for the earth to even realize that the sun is not there, because the light from the sun takes 8 minutes to reach the earth. So, your information that the sun is missing can't be faster than that. So, the sun is missing, this information will reach us after 8 minutes. And when you are looking at the sky, you will still be seeing the sun for those 8 minutes, even after the sun has actually disappeared. And then you realize, oh, sun is gone. Oh, now we are going, flying off. And it will seem very natural to you. Oh, the sun just left now, and that's why we flew off. For you, it is instantaneous, but for an outside observer, he knows this fool did not realize the sun was disappeared, and after 8 minutes, that information reached. For that outside observer, that person will know actually there was a time delay. But for you, you feel, oh, the sun is there, oh, light is there, light is coming, light went, oh, I am going to fly off because gravity went off. So that is the difference. That's what this paragraph is. Is that okay, everyone? I hope, Bhavish, this is also clear why it is independent of Q, because I just showed it to you over here, why it is independent, because no matter which derivation you go to, always you will notice that this Q and Q, which is the test charge, will always end up cancelling. You will always be left with the source charge, not the test charge. So it never depends on the test charge at all. Next information is about electric field lines. This is very simple. Let's talk about it. Ready guys? Ready guys? Ready guys? हाँ, फर्स्ट टाइम वाले भी देख सकते हैं डेफिनेटली. Now, if you look at this electric field lines, it's nothing but how the field is directed, and if you continue along that path, you will get a curve. That curve is called as electric field line. So, electric field lines were invented by Faraday. It's a non-mathematical way, it's just a graphical way because you like curves, graphs, pictures. It's called also line of force. He also called these field lines as the lines of force, because sometimes people often mislead thinking line of force means actual force is there. No, this is not force, this is field. Field is not force, they are two different things. The more appropriate term is actually field lines. Okay, so please do not use lines of force, although in a question they might use it, but it can be misleading because you might think it is actual force. It's a pictorial way of mapping how this electric field is around some charges, and it is just nothing but a curve which is drawn such that the tangent to it at each point is the direction of the field, net field at that point. Now, an arrow curve is obviously necessary to specify the direction from, because if you draw a tangent, the tangent can be this way also, this way also. So the direction of that arrow gives me the exact direction of the field. Now, what does this exactly mean? Imagine I have 2, 3, 4, 500 charges, God knows. These are the field lines. These curves are called as the field lines. If I happen to draw a tangent to these field lines, let's say I draw a tangent here. Let's say I draw a tangent like this over here. Then the tangent gives me the direction of the field. But when I look at the direction, you will be like, sir, is the direction like this or is it like this? Because tangent does not have any arrow. Then look at these curves. The curves have arrows. So the arrow is like this. So along the tangent go like this. This is the direction of the field at this point. If you draw a tangent maybe over here, then you will see at this particular point the field will be over here. So the tangent drawn gives me the direction of the field. Getting me, everyone? Same way over here. If I draw a tangent at this point, I can see the field will be either this way or this way. But to decide that, look at the arrow marks. The arrow marks are going like that. So the field will have to be in this direction. So the tangent drawn gives me the direction of the net field. It's a pictorial way of mapping how the field is around a charge or a system of charges. Okay, it's a simple curve. So simply put, for positive charge, we know how it is going to look like. For a positive charge, how it looks like. Then for a negative charge, how does it look like? Then how does it look like for just two positive charges? How does it look like for two negative charges, but let's say they are unequal? And how might it look like, let's say, for a positive charge with a negative charge? Different systems. Well, if you just go with a simple freehand drawing, this is how it looks like. For positive charge, yes, just radially outwards, nothing different, just radially outwards. For negative charge, radially inwards, that's all. For two positive charges, well, first outwards, but after that everything is curved, like this. no two field lines can ever intersect, you will notice. Even if it is too negative, still it will be like that. Now, when there is more negative charge as compared to this, you will see more field lines will be there on this charge as compared to this one. There will be more field lines here. So it will probably look something like this. Sure, you will see more and more field lines coming over here like this. Because this is more negative, so it will have obviously more number of fields terminating on that charge. Notice how from a positive charge always the field originates. Notice how on a negative charge the field always ends. Notice how the field lines never touch, intersect each other. Notice how the fields always try to be away from each other, they never want to intersect. Notice how more the charge, more is the number of field lines. Notice how when you are closer to the charge, the field lines are closer, and when you go away, then you will see the field becomes weak and the number of field lines around you also becomes less. All this is true. So all these are very interesting things or takeaways, I would say, from these diagrams. You should be naturally be able to draw these field lines and you should have a feel of it. That's what I would say. You should have a feel of it. So this is how the field lines look for different charge configurations. Is this clear, everyone? Everybody, yeah, getting a feel of what this field lines means? I'm so glad, Silis, you love my lectures and ma'am's lectures, and yeah, everyone. I'm so glad. Thank you so much. Thank you so much. Yeah. I hope Bhavish, Sindhu, your doubt was also clear. Yeah. Moving on to the next one now. So now let's look at the properties of all these charges. By the way, same thing, whatever I drew is there here. I didn't want to show you this because then that feeling will not come. Okay, you'll be like, ha, okay. No. Field lines start from positive and end at negative. First important property. The field lines start from positive and they end at negative always. We just saw that. Start from positive, end at negative. Start from positive, end at negative. End at negative, end at negative. Start from positive. Perfect. In a charge-free region, field lines can be taken to be continuous curves without any breaks. Makes sense. See, the moment there is no charge here, field lines are there. Continuously they are there. But the moment a charge comes, tuck, it ends. Tuck, it ends. Starts, ends, starts. So the moment there is no charge around, fields will continuously flow. This is like very obvious. So in a charge-free region, they are basically continuous without any breaks. Two field lines can never cross each other. Very important. The field lines never cross each other. And if they did, it would mean there are two tangents, two different directions, which is not possible only. How can you have two different directions of force at the same time? Either this or that. You can't have confusion. Electric field lines do not form closed loops. This comes from conservative nature. This is very interesting. Electrostatic field lines do not form closed loops. This is because it is conservative in nature, meaning you will never ever see a field starting and ending onto itself like this. This is a closed loop. You will never ever get that. Okay, for electrostatic fields. And this is because the field is conservative. What is the meaning of conservative, guys? Conservative means, so by the way, this is not possible. This is not possible for electrostatics. Not possible, but later on you will see it will be possible for electrodynamics. That's a different story. Anyways, conservative means, what is the meaning of the word conservative? Net work done in a closed path is always going to be zero. So if you start from a point and come back to the same point, the total work has to be zero. That is the meaning of conservative. Okay, we'll come to solid angle in a bit, but before that, also I think this solid angle concept comes because of this crowding nature. So imagine there is a surface and through that some field lines are passing. Here in that same area more lines, same area less lines. So per unit area there is less field, per unit area there is more field. So there is more density of field, more density of field. Here there is less density of the field, which means here it is a weak field. It's a weak field. Here it is a strong field. Here it is a strong field. Now actually you can see how this concept works for a point charge. Let's say I take a point charge like this and somewhere far away from it I take a surface, somewhere far away from it I take the same type of surface. You will see this is what will happen. Now observe this. These are electric field lines which are coming out from a charge. Notice these are electric field lines coming from a charge. Notice how when you are close, more number of field lines are piercing through that area versus when you are far, less field lines are piercing through that area. So when there are more field lines which are piercing through this particular area, can you see that? More field lines are piercing through this particular area. So I say there is a stronger field closer to the charge, closer to the particular charge. But as you are far away, the field strength reduces. The field strength reduces. So this is the concept of packing, closeness of the field. More closer they are, stronger the field, and it is also true everywhere here. When you are close by, you can see the density is more, stronger field. When you go far away, the field reduces. Here it is very strong, here it is weak. So looking at the crowding, you can get a sense of whether the field is strong or not. And now there are three possible scenarios which I want you to know, like this. This versus this versus this. This is empty space. In such an empty space, when there is no field, that's it. There is no field. Field value is 0. That's it. No lines, no field at all. In this scenario, the field lines are equally spaced. There is no strong, there is no weak. This is called as a uniform field. Uniform field, meaning the strength is the same everywhere, the direction is the same everywhere. This is called non-uniform field. Non-uniform field. In this case, you will see some places it is strong, some places the field is strong, some places it is definitely weak. That's the difference between uniform field, non-uniform field, and there is no field at all. There is no lines only. No field, no lines. There are no lines only, no lines of force or no electric field lines at all. 3 different scenarios. Is that okay? Right? Harsh, which part? Please let me know. So, coming back to this discussion, field always starts from positive, ends at negative. The tangent drawn is unique, so that's why no lines can intersect. When there is a charge, tuck, the field will stop, end or start from positive or negative, but when there is no charge, the field lines continue their journey. There are no breaks at all. And they will never form closed loops because the field is conservative. Why this is true, that you will understand in electromagnetic induction. This point for now just by heart it, but for now just keep in mind electric field is conservative in nature, just like gravity, spring, elastic forces, meaning work done does not depend on the path, rather it depends on the start and the end point. How you go there doesn't matter. If you happen to come back to the same point, then the total work done always, irrespective of how you come, will be 0. That is the property of being conservative. Forces like gravity, electric, elastic are conservative. Friction, viscosity, normal, tension, they are non-conservative. So even if you come back to the same point, you will not see the work done as 0. Okay, it will have some kind of positive or negative work. And in this case, we saw the closeness decides the strength of the field. So when you are closer to a charge, the field is more, they are densely packed. But as you go away, you can see less field lines are piercing. So you will see the strength reduces. So more field lines, more strong, less field lines in that same area, less field. That's the concept behind it. Clear, everyone? Okay. This is non-uniform because they are not equally packed. This is uniform because equally spaced. Nothing here, so there is no field. Now, what is this solid angle? You will probably need it at times, especially in Gauss law, sometimes, not very often, but just for the sake of it, it's very important that we know it. So, what is this concept of solid angle? I'll tell you. If you just take 2 lines, this is the center, this is your radius, then this is your arc, this is the angle. Now angle is theta, arc length is L, radius is R. And we all know how length of the arc is related. Length is R multiplied by theta. This is in meter. This is also in meter units. This is in radians, not in degrees. You cannot use this in degrees. This is what the formula is, correct? Standard. You have learned this before. Now, very similar thing happens. This is a 2-dimensional angle, by the way. This angle which you are learning, it is a 2-dimensional angle. There is also an angle in 3 dimension. You need to little bit visualize this. This 2D angle, remember it comes in a plane. The 3D angle comes in a, not necessarily a cone, but you have to take this yellow line and sweep it. Just imagine this is that line, sweep it across like this, not necessarily in a conical way. You can go like this, like this, like this, like this. Okay, that is then whatever is there inside of it, that is the 3-dimensional angle, like the one over here. So I take this line, I start rotating it, keep the center same, come back. So whatever is there inside, because remember this is going in not a plane, it's going in 3 dimension. Just imagine it went in 3 dimensions. So whatever is there inside, it will be a 3D angle. That is called as the solid angle. So solid angle is the measure of a cone. Usually they take it in terms of conicals, but it's okay. This is actually 3-dimensional angle. It's not a 2D angle, it's a 3-dimensional angle. So what's the difference? Just like you had length of the arc is r theta. By the way, solid angle usually symbol is sigma, psi, whatever you want to take. It's completely up to you. Here they have taken sigma, that's okay. Now you will not get an arc because it's a 3D angle. Think of it, you are enclosing an area. So if I go around like this and come, I can see on this side there is an area. Just think, I start like this and I do like this. So what have I covered? I have covered basically some area over here. Is that right? So if I start like this and I cover like this over here, so you can see there is an area which is enclosed. So that area is A, the solid angle is sigma, the radius is r. Then you will notice that the area subtended which is basically A, and the solid angle which is basically sigma is related like this, This is nothing but r square sigma. This is nothing but your radius. So r square sigma, instead of r into theta, it is r square into sigma. This is the formula to, think about solid angle most of the times. Now, if you take a line and rotate it exactly once, rotate it completely and bring it back over here. The total angle is 2 pi radian. Okay, you start like this in a 2D plane, you come back, the angle for one revolution is 2 pi radian. But here, it's not like you start here and just go around like this and come back. No. This is a 3D angle. Just think, it's like your scope. I can see here, I can see here, I can see here. This is my 3D angle. I can see in this zone. Now you expand it. You are looking here, It's like your vision where you are seeing. I am seeing literally everything. Up, down, top, bottom, everything I am seeing. I am then covering my entire 3D space. Then the total solid angle for the entire space around possible is 4 pi. Oh, by the way, the unit of this is steradian. It is 4 pi steradian. Okay, it is 4 pi steradian. Very, very important. 4 pi steradian. So think about it. If I take r radius and I move it literally everywhere, I take a gun, I start shooting literally everywhere, top, bottom, everywhere, radius r covering literally a sphere, that area will be the area of a sphere, which means r square into 4 pi is the area of the sphere. Very simple. 4 pi r square. Yeah, is that clear, everyone? Very good. So my dear warriors, similarly, if I make you visualize this example, if I take hemisphere, what do you think will be the solid angle? Remember, the solid angle is literally everything here, everywhere. This is the solid angle. So the solid angle in this case is 2 pi steradian. Because 4 pi means complete, but half of it I am removing. Exact half is 2 pi steradian. Getting my point, guys? Everyone? Similarly, I can make you visualize one last thing. Little difficult, but I will try my best. Okay? Like I said, it is a little difficult only, but still I will try. It's okay. Now visualize this. This is basically a hemisphere kind of cut into half. Okay, are you able to visualize this? Okay, not that great a diagram. So then, actually it's not come out well, it's okay. So if you take a hemisphere and cut into half, then the solid angle subtended will be pi steradian. Try to visualize that. Okay, so that's how this works. Is this clear? Everyone? Pakka? Okay, keep this in mind. Everybody, what if we keep conductor field will increase, decrease? We'll talk about conductors and field using Gauss's law later on. Okay, so that part will come. Yeah. Okay. Any other doubt, guys? Everyone? Clear? Pakka? Very good. Very good. Very good. Very good. Amazing. Very nice. Okay. One last thing over here, if at all you have been given a cone, let's draw a cone first. If at all you have been given a cone like this, and this then becomes your solid angle over here. Visualize this like this. This is your solid angle. Sigma, and let's say the semicone angle, this is the two-dimensional angle. The 2D angle is given as theta for a cone. Okay, this is the semicone angle, half of the cone angle, semicone, and this is nothing but your solid angle. Then this sigma is given by a standard formula 2 pi into 1 minus cos of theta. Just remember this, very important formula, can be useful for your JEE Advance. Not so much for mains, but for JEE Advance this can be useful. So solid angle is 2 pi, 1 minus cos of theta is a standard formula which you should remember. Okay, cool. So if theta is say 60 degrees, cos 60 is half, so 1 minus half is half, so 2 cancels, pi steradian will be the answer for a cone whose semicone angle is 60 degrees. Cool? Alright. So these are some concepts related to that. So these were the electric field lines, and we have spoken about electric field lines now. Field is always measured with a positive test charge. It is negative radially inwards, positive radially outwards. Next, field lines is a curve such that tangent will give you the direction of the field. The closeness indicates the strength. So if they are close, it is strong. If it is far, it is weak. They crowd in the regions where strong field is there, and they are far where the field is weak. When the field is constant, they are uniformly spaced like in uniform field region. Another important property, field lines are continuous. They are never having breaks unless there is a charge where it will originate or terminate. They will never intersect, and yes, they start at the positive and they end at the negative, and they will never form closed loop, like ending and starting at the same point is not possible. Okay, these were some properties which we have learnt. Okay, great. Now let's go to the next concept of electric flux, and then we'll go to Gauss's law. Flux. What is the meaning of this word flux? Okay, what is the meaning of this word flux? Flux means flow. Flux means flow. So imagine I show a cross section. And in that, some curves are piercing through it. It could be streamlines of water, it could be field lines of electric field, field lines of gravitational field, field lines of magnetic field, or just some curve, goddamn curve, God knows what it is, but something is piercing, man. I don't care. Maybe arrows are piercing through it. Okay, doesn't matter. And I show it like this, piercing at this and this point. Here also they are piercing, okay, like this. Here I find them going like this. They are not piercing at all. Here I will say there is flux but less of flux. Here I will say there is more flux. Here I will say there is no flux at all. Flux means flow. How much flow is there as these curves pierce through it? And this flux is always proportional to the number of lines which pierce through it. Number of lines which pierce through it. So don't get fooled by thinking that here more lines are there in a smaller area, that is why the flux is more. Wrong. This is a common mistake which students do. So just look at these scenarios. Over here is a very good example. Look at this. This same lines are continuing like this. Can you see there is more crowding here versus less crowding here? Yes, the field is strong. Strong field is there. Strong field is there. Here, there is a weaker field. No doubt about it. Weak field is there. But do you see the number of lines in this area? 3. Number of lines in this area? 3. That means the flux is same. So both of them have the same flux. So don't confuse flux with density. When you talk about density, that is field. The flux density is the field. Don't get confused. Flux is purely how much of it is piercing. More is piercing, better flux. Less is piercing, less flux. Both of them have same number, so same flux. Is that clear? So it's quite possible two places field is different, but the flux is same. It's also possible the reverse way. Flux is different and field is same. All of it is possible. Is this clear? Pakka? Everyone? Okay. Very good. Very good. So how do I measure flux, sir? What is the formula for it? Okay. As you can see over here, this is an imaginary area, not necessarily real area. Field lines are piercing through this area. So if I move this area, rotate this area, you will see some lines might miss piercing it. Right now this line is piercing it, but imagine I rotate it, this line will go unpierced through that area. If I make this area flat, most of the lines will go over it or below it, isn't it? Then there will be no flux. So it definitely depends on how you orient it. It also depends on how strong this field is, because if this charge was more, field is more lines will pierce, flux will also be more. Also, imagine instead of a big plate, I use only a small plate, then I will miss majority of the field lines. So my number will reduce, count will reduce. So my flux naturally will reduce. So that's why the flux depends on 3 things. How much area you are considering, how much strong is the field, and how are you orienting that area. These 3 factors. Is that clear? But now there is a small thing. We will not consider just area as area. We will consider area with direction, because area, how it is oriented. So I need area in directional form, so vector form. But sir, how do I show area in vector? Because area is flat. How can area on a flat surface be shown? I need an arrow. Oh, just draw up a perpendicular. So the perpendicular drawn, perpendicular drawn to this area gives me the vector of the area. It's a representation. Because a lot of people always think, sir, area sheet is like this. How can the vector be here? What is going in this direction? You are absolutely correct. Area is not going in that direction. I understand it. But if I have to show it as a vector, I need to show it as a line. I can't show it as a 2D plane. Because that's how vector is defined. Start and end points, direction. So I chose an unique way, and that is by showing a perpendicular to that surface. This is my surface. I draw a perpendicular, unique. That's it. Gone. Sorted. So the perpendicular will be unique and I will get a area vector. So area vector is always perpendicular to the surface, and if the area is big, this vector will be big. If this area is small, the vector will be small. If there is no area, zero length. So bigger the area, this vector length will increase. That's how you visualize it. It's just a representation, not something actually in that direction. Okay. So having said that, what is the magnitude of this flux? How do I calculate the electric flux? What is the formula for it? It's straightforward. I will just show it to you. This is my area vector, which is perpendicular. This is my surface through which I am measuring my flux. The fields will pierce through this. Maybe there is a field going like that, maybe like this, and so on and so forth. These are your electric fields, electric field lines or electric field, okay, and area vector and the field vector will make some angle, and that angle I will call it as theta. That angle I will call it as basically how much? Theta, my dear students. Okay. Please keep in mind, this is a common mistake. Theta is not the angle between the surface and the field. It is the angle between area vector and the field. What do I mean by it? See, imagine guys, this is the area, okay, this is the surface. This is the surface, everybody can see, okay. I'll keep it like this. Now, imagine the field is coming like this. Lot of people, field is coming exactly perpendicular like this, okay. Lot of people are going to say, sir, the field is making 90 degrees with the area vector. Wrong. Think, if this is the surface, the area vector will also be like this. Field is also going to be like this. So actually field and area vector are parallel. That means my theta will be 0. But yeah, with the surface I make 90 degrees, but with the area vector I am making 0 degrees. Is that clear? Similarly, imagine my field is going like this. Then a lot of people think, sir, theta is 0 because you are going parallel. No sir, field is in the plane. Wrong. Yes, field is in the plane, but with the area vector, I am making 90 degrees. So theta will be 90. So be very careful. There is a difference between surface and the vector of area itself. Got it? Okay. Now the flux attaining, no, what is the meaning of flux attaining equilibrium condition? Flux is just the flow. It's an imaginary thing. Okay. It's not like there is a physical line, physical thing which you can feel and sense that, oh, this is the flux. No, flux is just an imaginary quantity which you have created like electric field. Okay. All right. To experience it, you need something else. You can't experience on its own. For field experience, you need a charge. Then you experience a force. Okay. So the flux, my dear warriors, the electric flux has a symbol of phi. Okay, this is your electric flux. Electric flux, and this flux, my dear warriors, is given by electric field into cos theta multiplied by area. But field and area are vectors, and there is a cos. Naturally, there is a dot product and output is a scalar. So you will see this is electric field dot producted with my area vector. So there is a dot product involved over here. So this is the formula. This is simple form. This is the vector form, nothing else. Yes, electric flux is a scalar quantity. It does not follow the rules of vector addition. If you want to know the units E and A, E is nothing but Newton per Coulomb. Area is meter square. So Newton meter square per Coulomb, one of the units. Or remember, volt per meter was also a unit. So volt per meter into meter square. One of the meter will get cancelled. So you will just get volt meter. It's not volt meter the device. It's just volt into meter, not to be confused with the actual device. So that's how you measure the electric flux. Simple and plain. But now it's not necessary that my area is always going to be smooth, flat. And it's also not necessary my field is uniform throughout. So this formula that I just mentioned is only valid. This formula which I mentioned is only for uniform fields. Uniform field and flat surfaces, which is not always the case. If it's a curved surface, if the field is changing, then what do? Then you need to do integration. And I'll tell you what is that integration going to look like. So if you take some curved area and you take a small patch of it, this is your small patch, guys, as you can see over here. In this small patch, there is a small area vector, and that small area vector I'm going to call it dA bar. dA bar. At that point, locally, there is an electric field which is present, which is E. So the flux through that element, so the flux through the element, will be also very, very small, and it will be given by electric field dot producted with that small area. But imagine I have a big area, and that area is a closed area, meaning I have covered literally every patch of this. There is no opening left at all. So I cover literally everything. So if I measure the total flux through a closed surface. A lot of people sometimes have understanding issues with closed surface. I'll give an example. So for that, I have this shirt. It's also made of some cloth, and I feel that this is an open surface. You can see there is an opening here. There is an opening for my hand, another opening for my neck, and another opening for my other hand. So many openings, right? So this is definitely an open surface. But imagine I stitch this off. Whatever this near my waist, I stitch this, whatever this is there, I stitch this off. My hand's opening, I no longer take it, I stitch it. My neck opening, I stitch it. My this opening, I stitch it. So whatever will be there, I know it will feel like a balloon then. So that is a closed surface. There is no opening involved. Is that clear? What is the meaning of a closed surface? So in such a case, the total flux integration will be there, but you denote that integration with a circle like this. So you put cyclic symbol. That is just to tell ki bro, consider everything. Don't leave one thing also. It's a closed surface. So that will be closed surface flux, total flux, and I will write it down as integration of E dot dA, cyclic integral. E dot dA, cyclic integral. That's all. So this is how you measure total flux of a closed surface. So flux closed, integration of literally everything, E dot dA. Clear till this point? When is flux maximum and minimum? You take the same surface like this versus same surface like this. In this case, the field lines are going from top and from below like this. See if you are able to visualize this setup. They are going from top and below versus over here, these field lines are piercing. They are piercing. In this case, notice how the area vector is parallel to the field. In this case, the area vector is perpendicular to the field. In this case, obviously, theta is 90, so cos 90 is 0. So the flux is minimum. In fact, it will be 0 magnitude wise. But sign wise, if you take negative value, then that negative can be as negative as you want. So there is no end to it. I am talking only about the magnitude aspect. And otherwise, the maximum flux is over here. Yeah, correct. Because theta is 0 magnitude wise. This is magnitude wise maximum flux. Is that clear? Because maximum field lines will pierce here. Nothing is piercing 0 at all. Cool? Okay, great. So that is what is there over here, guys. In your NCERT also, same thing has been mentioned. For a closed surface, the total flux is E dot dA integration cyclic. Cyclic stands for complete surface. Not even one thing is remaining. Cool. So let's start with some questions coming up on your screen. A field is parallel to the surface of A. What is the flux through it? Very laddu question. Come on. Oh, I will turn on the poles. Yep, 30 seconds for all of you. A field is parallel to the surface. What is the flux through it? Very simple. So, if you see our surface, if it is like this, the field is parallel to the surface, meaning like this. Meaning, if you show the area vector by any chance, the area vector will be like this. So, lot of people make this mistake. They think parallel means 0 degree. Wrong. It is 90 degree. So, if you try to measure the flux, flux will be E into cos 90 into A. Cos 90 is 0. The flux will be 0. Answer is 0, my dear warriors. Answer is 0. Okay, which is basically option D. Okay, I don't know, some of you missed the polls or what? Yes, the answer is D. Now let's do another interesting question on flux before going to dipole. It's a very nice question. This proper JEE advanced type question could be asked in single choice or I don't know, multiple choice or match the following, God knows. Now imagine there are XYZ axis This is X, this is Y and Z, and there is a kind of a weird area which has been made like this. And the coordinates of these points have been also mentioned. This point is A, 0, 0. This is 0, A, 0. This point is 0, 0, A. One is on Z, X and Y axis. So see, if you are able to visualize, there is a beautiful area which is formed if you connect these 3 points, which is a 3-dimensional triangle. Everybody getting this? Okay. Now in this space, it's mentioned the electric field is E naught I cap. Actually, you can put J cap also, anything, still procedure will be same. Find the flux through that particular area. Very interesting thing. So a lot of people will be like, oh my god sir, 3D problem, area vector in 3D, how to measure the angle, do we need 3D geometry, god knows what. But my answer is simple. Don't go to very complex mathematics. Think normally, you will get it. See where the field is. E naught I cap, that means it is parallel to the x-axis. Okay, let's go there. It's parallel to the x-axis, so it is going like this. It's piercing here. It's also probably piercing here. It's also probably piercing here. It's also probably piercing here. And so on and so forth. That's how the electric field is. E naught in magnitude in the x direction. Now, think. Whatever field lines are piercing here, that will give me the measurement of flux through it. If only I could know any other area which has the same number of lines as that of this triangle, maybe I will be able to figure out the flux easily. Only if I could have another convenient area, not this 3D weird area, I would be able to solve this in a much simpler manner. Think. I think there is a place, there is a area which has the same number of lines which goes as in this 3D weirdly oriented triangle. Just look at this shape over here. Just look at this shape over here, which is in the YZ plane. Just imagine this. Yeah, it's very interesting. The same line will be over here, and that same line, visualize, it will basically come and pierce this triangle from behind. It will come and pierce this triangle from here probably. It will come and pierce this triangle like this. This will come and pierce this triangle over here. So try and visualize this, guys. Try and visualize this a little bit. This is coming like this here. This is coming like this somewhere here. Just try to visualize this a little bit. Can you now see? Yep, this point, this point, this point, same triangle has that same lines piercing through it. So can I say this particular triangle, the triangle in YZ plane has same flux as the flux in the triangle in 3D, which is required, which I require it. Same flux is there, same lines are piercing through it. So I have solved the problem to a much easier question. So now my triangle is basically just this. In that, this is my base, this is my height. Keep in mind, this is your Z axis, this is your Y axis, and the electric field naturally is perpendicular over here. electric field is naturally perpendicular over here, and even the area vector, if you see, is like this only. The area vector is also in that same direction. So angle is 0 between the field and the area vector itself, and the area vector is half into base into height, a into a, so it will be a square by 2. Angle between them is 0. My problem is solved. So it will be just nothing but E naught multiplied by cos of 0 multiplied by area. So cos 0 is 1, area is a square by 2. So it will be E naught a square divided by 2. That's the flux. Simple and sweet. It's not a complex question after you visualize it. How many of you were able to visualize this? Yeah? How many of you were able to visualize this? That actually this 3D area is somewhere here. It's in 3D space. But that triangle, that pink triangle is behind it in YZ plane. Same lines will eventually pierce the blue one. Yeah? Clear? Amazing, amazing. Great. Anyway, so that was all about the flux. Now, one last concept before moving ahead. That is over here. A lot of times people ask me, sir, is flux going to have negative and positive values? The answer is yes. Now, some of you missed asking me that doubt. I was surprised nobody asked. Sir, you can draw perpendicular this side also, no? Absolutely right. So, area vector can be this way or that way. Oh, so what is right? Both are right in their own way. It's just that one value will be positive, one value will be negative. For flat surface, it's okay. It does not have so much of meaning or not so much of sense to it. But for a closed surface, you do not get two options. You have, but we limit the option by convention. Meaning, we always take an area vector. We always take the area vector outside only. We always take it outward. Area vector is always outward by convention. By convention. Keep this in mind. So, if there is a field which goes like this, then the flux is going to be positive. But if there is a field which goes inside, then the flux is negative. So keep this in mind. For only closed surface, there is a convention. Outwards is positive always, and any field which goes outside will be in the direction of the area vector. So it is positive. Opposite to it, it is negative. So that's the convention. Only for closed surface. Okay, but for flat, you can take any direction. It really doesn't matter. We are more interested in the magnitudes of it. Magnitudes of it. Looks like we are going to reach till 12 o'clock today. Right. So let's complete electric dipole. It's very simple, and then we'll take a short break and then again return. Okay. Come on, let's do this. Electric dipole is nothing but two equal and opposite charges separated by a small distance. That's it. That's a simple definition, nothing great about it. So if we have two charges but equal amounts, 2 Coulomb minus 2 Coulomb, 5 Coulomb minus 5 Coulomb, minus 6 microcoulomb plus 6 microcoulomb, always equal and opposite. So a pair of equal and opposite charges by some distance is called electrical dipole. Now that distance is given by 2a, the charges are given by q and minus q. So if one is positive q, the other is minus q, and the distance between them is taken as 2a. This is deliberately done because the midpoint, if the dipole is here, from midpoint this is at a, from the midpoint this is at a. So the total distance will become 2a. That's a deliberate reason, nothing else. Otherwise you could have taken a only. There is no great thing. Now, a lot of people think Sir, if you have equal and opposite charges, then if you take it as a system, won't it behave like a zero charge? Yeah, you feel that it behaves like a zero charge because positive and negative should cancel, but actually the positive and negative are not at the same place. They are separated by some distance. That's what makes this concept interesting. If positive and negative are at the same place, yes, it will be like a zero. But the moment you separate them, can you see, in fact, they are producing electric fields from positive to negative, positive to negative, positive to negative. So around it, there is an electric field. It's not like there is no field now. So that's what makes this case interesting. Awesome. So they do not cancel out. So there is some electric field around them. There is some electric field around them. So what is the electric field? Before mentioning that, there is a particular quantity which talks about how strong or weak a dipole is. So if you have a dipole, distance of separation 2a, then you get a new quantity called as the dipole moment. Now this dipole moment is always a vector quantity, and that vector always goes from negative to positive. Be clear, not positive to negative. Positive to negative is what the field goes. Negative to positive is what the dipole moment goes. Oh, okay. Dipole moment is a vector which goes from the negative charge to the positive charge. This is first important thing. The symbol of dipole moment is P. The magnitude is just given by any one of the charge, let's say Q or minus Q. Take the magnitude of it, multiply it with the distance between them. So strictly speaking, the dipole moment is nothing but any one charge, any of the charge magnitude wise multiplied by the separation between them. Units, very easy. SI unit. Charge and distance. Charge is Coulomb and distance is meter. So Coulomb meter is the unit of this dipole moment. Very simple and straightforward. Clear till this point? Okay. Now that you realized, okay sir, dipoles will create a field around it. It's not zero field. That's 100%. I can see it from here. This does not mean that the field of electric dipole is zero. So in fact, they do not cancel out. That's one thing. And we defined what is dipole moment from negative to positive. Now you will see where dipoles really come in real life. You might have learnt about this in chemistry. H2O is a polar molecule. What happens is oxygen develops the negative charge and the two hydrogens have a delta positive charge. The electron cloud has shifted to the oxygen, and in this process, obviously if few coulombs went here, an equal amount of positive charge has developed on the hydrogen. So actually speaking, there is a dipole here. There is also a dipole here, negative and positive. Even a carbon dioxide molecule is a molecule with two dipoles within it. Carbon has that positive delta because the electron cloud has migrated to the oxygen molecules. And because this charge and this charge is same, so it's a dipole. This charge and this charge is same, that's also a dipole. So most of the molecules around us have the electron cloud migrate from one side to the other side, which creates equal and opposite charges, which makes it a small teeny mini electrical dipole. And this makes a whole bunch of difference because how these molecules react to electromagnetic fields decide a lot of properties of these materials, like the dielectric constant, dielectric material, all these things depend on these polarities. So in case of oxygen and hydrogen, basically H2O molecules, you will see that oxygen is negative, hydrogen is positive. So there is a dipole moment, which is like this, and there is another dipole moment which is like this, correct? From the negative to the positive, negative to the positive, two dipoles are there. Whereas in CO2 molecule, you will notice negative to positive, negative to positive. So there are two dipoles like this, negative to positive, negative to positive. Can you see that? Two dipoles like this. Now, since dipoles are vector quantities, so they can add vectorially, is that right? So if you add these two dipoles moments vectorially, you will get a net dipole moment. You will get a net dipole moment, which is obviously not zero. But in this case, these dipoles are equal and opposite, so the net dipole moment cancels out and it is zero. So whenever the net dipole moment is not zero, it is said to be a polar molecule, whereas when the dipole moments cancel, it is said to be net polarity is zero. Net dipole moment is zero. So that's why H2O is a polar molecule, whereas CO2 net dipole moment is zero, so non-polar as a whole. Is that clear? What is the dipole in? We'll come to that. Hold on, Bhavish. We'll come to all of that. Hold on. Is this understood? How in real life dipole moments play a role. So, what was a dipole? Two charges, equal and opposite, separated by a teeny mini distance, but the field is there around it. It's not behaving like a net zero charge. And the dipole moment is any one charge into the separation between them. And we then saw that most of the molecules around us, the dipole moments either add or cancel. If they add, it's a polar. If it's not, it's non-polar. And that's how the physical significance comes into play. Is that clear, everyone? So even CH4, it's going to form a tetrahedron CH4 structure. Remember, CH4 equal dipole moments in 3D space. It forms a nice regular tetrahedron. So all the dipoles cancel out and it becomes a non-polar molecule as such. But H2O and so many other things, right? They are not going to be non-polar. They are going to be polar in nature. Perfect. So, sir, now tell me, what is the electric field? What is the electric field around a dipole? Let's talk about that. So these are the rough field lines because of an electric dipole. Now this line that I have drawn, which passes through those dipoles, that is called as the axis of the dipole. This yellow dotted line is called as the axis of the dipole. Needless to say, the dipole moment is going to be like this. This is how our electric dipole moment will be vector. If you draw a perpendicular to this axis, which bisects it from the midpoint, then that line is called as the equator. It is called as the what? Equator. Till this point clear? Very good. Now you go to any random place, doesn't matter where you go to any random place. Let's say you are going over here. Now that point from the midpoint of the dipole is at a distance of, or making a position vector of r, making some angle like this over here. At this point, if you notice, the electric field line is going like that. So 100% the electric field will be over here like this. The electric field will be over here like this, tangent drawn to it. It's not perpendicular to r, it's just some random direction. Why will this electric field come? You think. Simple, superposition principle. From this positive charge, you are at some distance. From the negative charge, you are at some distance. So the positive charge is going to apply an electric field like this. The negative charge is going to apply an electric field like this. These are the two fields due to the negative and the positive charge, and the vector sum of both of them will be your net electric field. Yes or no? The vector sum of these two electric fields will be your net electric field. So can I say my net field around a dipole, due to a dipole, is nothing but the field due to the positive charge and the field due to negative charge. This is by superpositioning principle. Now you need to apply geometry, Pythagoras, approximations, binomial, whatever you want to apply, you apply, and then you finally get the answer. We're not going to waste our time in that derivation, but you understand how it comes from and where it comes from. Is that clear? So this positive charge will push it like this, this negative charge will pull it like this. Adding them vectorially will give me the net field, and you can see it is exactly along those field lines. At different places, the field will be also different and in different directions. So what's the generic formula for that field line? So let's talk about it. What's the generic formula of that particular field line? So if I am here somewhere, this is the position vector. This is the position vector making angle theta. This is electric field. If you continue that position vector, it goes like this. Okay. So the magnitude of that particular electric field in general around the dipole is given by Coulomb constant 1 by 4 pi epsilon naught. Okay. And then you have that dipole moment over here, and then you divide it by r cube. Yes, divided by r cube, that means how far you are from the dipole, and then multiply it with root of 3 cos square theta plus 1. Root 3 cos square theta plus 1. This is the generic field at any distance, at any angle. And how it is oriented is dependent on this angle alpha. What angle it is making with the position vector. So I'll call it alpha. And this tan of alpha is simply tan theta divided by 2. It's not tan theta by 2, it's tan theta whole thing divided by 2. So you get the direction and the magnitude. This is the generic answer, guys. You should know it. Okay. This is the God formula. This is the generic God formula. Now, there are two special cases in it. What could be the two special cases? Already I have marked it. You would get an idea now. See, one special case is when you are on the axis. So on the axis, meaning the electric field on the axis is over here. And if you are on the equator, the field will go like this, isn't it? Or field will come like this. This is electric field on the equator. What's special on the axis? What's special on the equator? Simple. Let's talk. If you are on the axis, then the point lands here. This position vector falls on the axis. This angle collapses to 0. So theta is 0. Not necessarily. Actually, this is also an axial point. So if you are here, then this position vector comes like this, and then the angle becomes 180 degrees. So it is 0 or basically 180 degrees. In such a scenario, try to mentally substitute. Cos 0 or 180 is 1 or minus 1. Squaring it will make it 1. 1 into 3 is 3. 3 plus 1 is 4. 4's root is 2. Oh, so 2 will come. So that means the field on the axis will be 2kp divided by r cube. 2kp divided by r cube. Is that absolutely clear? Everyone? Why that 2 came? Because theta is 0, you can substitute it. But let's say you are on the equator. On the equator. What is so special about the equator? Theta. If you are on the equator, angle is 90. The position vector will make 90 degrees. Even if you are here, still it will be minus 90. Now cos 90 or minus 90, it is anyway 0. So 0 into 3 is 0. 0 plus 1 is 1. Root of 1 is 1. So it will be, by the way, plus minus 90 degrees. Okay. So the field on the equator will be, just P will come. So it will be K into just the dipole moment divided by R cube. That's it. That is the answer. Is that clear, everyone? On the axis, the field is 2 times the field on the equator. Does it make sense? I think it does. Why? If you are on the axis, these field lines are close enough. Whereas on the equator, these field lines are distributed far away. So the density is more, hence it is stronger. When you come here, equator, far away, field becomes weak. So that's why on the axis, if you ever forget, think of how the field lines look like. We just have drawn it over here. Yeah, it's strong here, whereas you come here, they are far away, so it becomes very weak. Now, by the way, whenever I show these formulas, there is a very important thing which you should know, and that is this. In these formulas, my distance is much larger than A, basically this distance, or basically this 2A, meaning it's a short dipole. Only then you can use this, because there are lot of approximations which go on when you solve this, try to derive it, and those approximations are valid only under this assumption. So keep this thing in mind. It's only and only when your dipole is small and you are far away. Like the dipole length is in millimeters and you are at few centimeters. Or the dipole length is in centimeters, you are in few meters. That's what it is. Okay, clear? Okay, all right, amazing. So keep these things in mind. Now one small thing over here, if I write it in vector form, how will it look like? Look at this, axis field is in this way and dipole moment is also in the same direction. So same direction, parallel. So if I put P bar, E bar and P bar will be in the same direction. But the moment you go to the equator, things change. Yes, things will change. How, sir? Electric field at the equator. What else is going to change? Observe. This field at the equator is this way, dipole moment is the other way, opposite. Hence, you will see that there will be a minus sign if you put a vector form. Otherwise, magnitude wise, it's just Kp by R cube. One more thing to notice, how the field is no longer proportional to R square, but it is proportional to R's cube instead. Okay, so those are some interesting things to note. Direction, magnitude, how it is double, how it is inversely proportional to R cube instead of R square usually. Okay, so all these are important things. Alright, same thing has been put over here in NCERT, 2p by R cube or minus p by R cube. 1 by 4 pi epsilon naught is your Coulomb's constant. Same thing is there in NCERT. Dipole moment is charge into the length. So let's solve some questions. One of these questions is here. A short electric dipole. Yeah, this is the question, or yeah, okay. A short electric dipole, the magnitude of the electric field at a distance r on the axis to that on the equatorial line. Just imagine this question came in 2020. Let's do a poll quickly. Come on, what's the answer for it? If you talk about electric field on the axis versus electric field on the equator, I just told you this is double of this, and the formula was also there, no? 2kp divided by r cube versus just kp by r cube. So everything else cancels, but 2:1. So the answer is 2:1, guys. It's double on the equator as compared to the axis. Double on the axis as compared to the equator. So 2:1 is option C. And yes, very good. Many of you have done it hopefully right way. Okay, so C is the right answer. Very laddu question. Now let's do this another question. Yeah, it says 4 point charges are there and they are placed on the y-axis at some distances. What is the field at a large distance on the x-axis? Where is asymptotically as? So when you are very, very far, how will the field change? Yeah. Come on. B, A, C, D. Let's draw the diagram. Best. Draw the diagram, guys. This is your y-axis. This is your x-axis. Okay. Now, where are the charges? Minus 2d, minus d, plus 2d. One is here, one is here. Minus q at, okay. Minus q plus q, minus q plus q, minus q plus q. Oh, just check this out. Y is equal to plus d is also one second. Minus 2d is minus q. Y is equal to minus d is plus q. Y is equal to plus d is plus q. And this is minus q. I hope this was the right question. Okay, fine. And the question is, if you go very, very far away, that means somewhere here, like this, what will be the force going to look like? Very simple, guys. Now, I hope you can see there are actually two dipoles here, minus q to plus q. There is a dipole like this. Can you see? There is a dipole like this, and this is also a dipole. So, two dipoles are there in this format. So, what do you think will happen? Come on, think, guys, what should be the correct answer? What should be the correct answer? Pakka, B. Because sir told it will be inversely related to the cube of the distance. But that is where many kids go wrong. See, this is x, I understand. But this dipole will give a field in this direction. This dipole will give a field in the other direction. So actually they should cancel out. Actually they should cancel out, isn't it? But will it? I don't think so. It won't cancel out. It won't cancel out. I'll tell you why. Because there is going to be a small difference because of this small gap over here. Because of this small gap over here. Yeah, it won't exactly cancel out because these two dipoles are not exactly at the center. If they were exactly at the center, they would have cancelled out, but now it will not. If you want to treat it like a dipole problem, be my guest. But instead, you can do one simple thing. Just take this very, very far away point, very, very far away point like this, very, very far away point, and just try to see what is the electric field at this point in the y-axis due to this charge, what is the electric field due to this charge on the y-axis at this point, and so on and so forth. You do that and you will notice a very interesting thing, that it will not be proportional to 1 by x cube, but rather x raised to 4. It's a very interesting thing. I will give you this question as homework. Okay, try this out and I'll tell you the hint for it. So imagine this is basically your D, this is basically your X, and your electric field due to this charge will be in, let's say, this direction. You only will have to take this component, vertical component. Okay, just take the vertical component. Okay, and then also choose the horizontal component. You will notice this charge mirror image will create a field like this and a field like this. These vertical components will cancel. This charge and this charge, both fields like this and this will cancel. Only this will remain. Only the X component will remain. Can you see that? So that is what is going to give rise to the net field. So the net field will be only because of the X component. So only calculate how much is the X component and mention this as angle theta. So even this will be theta. So how much will be EX? EX will be how much ever your electric field is. It will be E cos theta, and E will be nothing but K Q divided by this distance, which is D square plus X square root square. So it will be this only, and cos theta will be adjacent by hypotenuse, which means X divided by D square plus X square under the root. Then you assume X is much larger than D, use binomial approximation, and basically if the field due to one charge is like this, you know due to other charge, instead of D it will be 2D. That's the only difference. So when you add all of them, you will notice a very interesting thing. This electric field is going to be proportional to X raised to 4. Okay, that's what you're going to probably see. Ex is equal to Ex cos theta. How? See man, like this. Our charge is here. The field has to be along this line. So if the field is like this, if this is basically your electric field, this is your angle. So how much will electric field in the X direction be? Because then this will be my theta, opposite angle, correct? This will be theta and this will be Ex. What happened to the other component? The other component this will anyways get cancelled. Ey will anyways get cancelled. It will get cancelled by the other charges Ey component. So don't worry about it, only concentrate on the x component. So that's how you need to do it. Cool guys, everyone, pakka? Yeah. Asymptote means as x varies asymptotically means x is very far. X is very far. That's all. Okay, so we have seen all these things. Electric field on the axis, electric field on the equator, and 1 by r cube is a very interesting parameter which we saw for an individual dipole. But if you have multiple charges, then you know things can change. Anyways, now one last thing over here before going ahead is how do these dipoles behave? How do these dipoles behave under another external field? Very interesting. So, if you take a dipole, meaning this is negative charge, this is positive charge, this is your dipole moment, and you place it in somebody else's electric field, this is external. Please note, it is not the field which is created by this dipole. That is completely different. I am talking somebody else is there who is creating an electric field. How will this dipole interact? Because think about it. We said the significance of dipoles is in molecules. So imagine you pass some electric field through a beaker containing some water, or some gas is there and lightning strikes, there is electric field. These molecules will experience electric field's force. How will they rotate? How will they move? That's what I'm trying to understand. Because there is some rotational aspects to this, and because of those rotational aspects, a lot of medium properties change. That's the whole purpose of studying this. So these dipoles will experience force, and we just spoke about it. If there is a positive charge in the field, the force is in the same direction. Negative charge in the field, the force is in the opposite direction. So this force is the charge multiplied by the field. This force is also the charge multiplied by the field magnitude wise. Now, whenever you have two forces which are separated by some distance, whenever you have two forces separated by some distance, that means they are not collinear, then such a force or pair of forces is called as couple force. Why couple? They are same but opposite. Pandu, Champa, positive, negative. Force, force, opposite, couple. So that's a couple force. And always a couple force will create a torque and will always create a couple torque. Couple torque. Couple torque. How much is the value of the couple torque is not a big deal to figure out. Okay, that couple torque always happens to be any one of that force multiplied by the distance of separation. Multiplied by the distance of separation. So this concept is very important when you study electric dipoles. Okay, it's one of the forces into the distance of separation is the torque which is created. It will try to rotate it. So in this scenario, what happens is, if you measure the distance, it's very easy. It's actually this distance. And how do I get that distance? Not that difficult. Okay, we already know the length of a dipole. The length of a dipole is basically 2a. The length of a dipole is 2a. This was dipole moment, and this is that distance. I will call it as d. So if I want to measure the torque, my dear, the torque will be force, whatever is the force, multiplied by the distance, which is in this case d. the value of the force is Q into E. Okay, Q into E, fair enough. The distance, not difficult. P and E are making some angle. Okay, if that is theta, even this is theta. So it is hypotenuse sine component. So it will be nothing but 2A multiplied by sine theta. I'm just going to rearrange all this stuff. How? Observe. I will write this as Q multiplied by 2A separately. Then I will keep electric field separately. And I will keep sine theta separately. And this is what is my torque. Now I quickly realize what is this number. Q into 2A, charge into the distance of separation. That is my dipole moment, isn't it? This is simply electric field, isn't it? And this was sine theta. I have got the magnitude of the torque. Magnitude of the torque. Magnitude of my torque. Perfect. But this looks to me like a vector equation. Dipole moment vector, field vector, sine theta. This is also vector. So there should be something like a cross over here. Yes, there is a cross. It is actually dipole moment cross the field vector is your torque. Is your torque. So torque is a dipole moment cross the electric field. That's how you get the torque. PE sine theta. Okay, very straightforward. Now this torque is minimum. This torque is minimum if they are aligned. So torque is minimum and it is 0 if my dipole moment is aligned with the field vector, because sine 0 is 0. It's also possible that my field is here and dipole moment is exactly opposite, meaning 180 degrees. So sine 180 is also 0. And the magnitude is maximum when the dipole moment is basically perpendicular to the field. So when you are perpendicular, sine 90 is 1 and the dipole moment will create a maximum torque. Okay, maximum torque. All these things clear? Great. One last thing over here. Always whenever there is a couple force, this and this will cancel. Net force is always 0. Net force is always a big fat 0, guys. Torque is there, but net force is not there. Always. So in a uniform electric field, this was not just any random external field. This was a uniform and it was external field. The torque is P cross E, net force is 0 and the torque is minimum when it is 0 aligned, and if it is 90 degrees it's maximum. How it impacts our molecules? Let me show you. Imagine this was our H2O molecule. Negative, positive, negative, positive. We just saw there is a net dipole moment like this, isn't it? There is a net dipole moment like this. This is a polar molecule. Now imagine you place this water in some electric field, in somebody's external electric field. Can you see dipole moment is here, field is here, torque will generate. Immediately there will be a torque on this oxygen molecule and the torque will rotate the molecule until it stabilizes, and you will see finally maybe the molecule becomes like this, and then you will notice the net dipole moment is here, which is in the direction of the external field, and then you might find that this molecule is in equilibrium. You will find that this molecule is in equilibrium. So it will try to align all the molecules of the water in that same direction. Just because you have turned on the electric field, the torque will rotate it. But if it was not polar, nothing will happen. It will chill. Nothing will happen. Only because of that net polarity, it has realigned itself. Got it? Everyone? Amazing, isn't it? Alright. Now, sir, what happens if I take that same dipole, but instead of uniform field, the field is not so uniform? Oh yeah, that can happen. This is your electric field. It is not uniform. Here, as you can see, it is strong. Here it is weak. And you can also notice how the force are not really cancelling out. Here the force is smaller. Here the force is strong. This is F negative. This is F positive. F negative is not equal to F positive even magnitude wise. So the net force is not zero. Okay. And net torque anyways will come. As you can see, this force and this force might create some torque. So the net torque is also not zero. So only when the field is uniform, the net force is zero. Very, very important, guys, this line. The net force is zero. But torque is there or may not be there depending on the orientation. But when you say a non-uniform field, there is going to be a net force and torque might be there, not be there depending on the orientation. So very important line. Dipole experiences a net force if the field is not uniform. Okay. There will be in general a torque, in general, because not necessarily all orientations, like some orientations there might be equilibrium, no torque at all, but force will 100% be there. So this is non-uniform external field. Cool? Okay. Let's see. There was a question which was asked. An electric dipole is placed at an angle with some field, experiences a torque, the length is so much, what is the charge on it? Yeah, this is the detail in which I go, guys. I'll make sure all the points are covered in that chapter. So anybody watching this lecture at any point of time, even if you watch it after 2 hours, 1 hour, I want everybody to get the same kind of quality content. So this chapter, anybody, trust me, has a doubt whether from boards or JEE perspective, if you are watching this lecture, your doubts, concepts and application of formulas will be clear. Alright, let's have a look. So what are we given? Angle, field, torque, length, charge is asked. Torque, magnitude wise, is P sine theta. Okay. But P is charge into the dipole length. So 2A into E into sine, what is that angle? 30 degrees. Torque is already mentioned as 4. Charge I don't know. Now common mistake in these questions, people write dipole length A as 2. Wrong. A is not 2. A is actually 1. Rather 2A is 2 centimeters. This is the total length of the dipole. So that's the most common silly mistake in these questions. So 2A is 2 centimeters. So minus 2 meters. Field 2 into 10 to the power 5. And what else? Sine 30 is basically half. This 2 and this 2 cancels. This 2 and 4 cancels. It will become 2 Q into these 2 have gone. Minus 2 and plus 5 will make it plus 3. That's it. So Q will become 2 into 10 to the power negative 3 coulombs, which is 2 millicoulombs. So 2 millicoulombs is option A. That is the right answer. Option A. Very good, May. Calculator. Why do you need calculator, man? For this? Yo. Why you need calculator, man? You don't need. That is the answer. Okay, so these are questions on torque, force. We've seen this. Summary also we've seen. Now let's study centipede. This looks like a centipede, guys. My God. We are coming towards Gaussian application. Very nice it is. Visualization is good. So over here, yeah, before we go to Gauss law, there are three geometries which you should know. And in these three geometries, we will be calculating the fields in a bit. But before going there, you should know how the field is written. How the charge is written based on the geometrical shape. See, if you take a wire and you put charge on it and that charge gets distributed uniformly, then what will be same? Per unit length, the charge will be same. That's exactly what this is. Charge per unit length is called linear charge density. What is it called? Linear charge density. Lambda unit will be Coulomb per meter. How much charge is there? If you take a meter, there will be lambda coulombs of charge. If you take 2 meters, 2 lambda, like that. So that is the meaning of linear charge density per unit length of the wire. If you take a sheet, surface, this is a surface, then per unit area, how much charge is there? That is your surface charge density, sigma. Charge per unit area, Coulomb per meter square. Coulomb per meter square. We take a meter area, 5 coulombs of charge is there, 5 coulombs per meter square. That is sigma. Lastly is volume charge density or just charge density. Sometimes it is called rho. Charge per unit volume. You take a unit volume inside, and in this unit volume, how much charge is there? That is charge density. Unit will be Coulomb per meter cube. It will be Coulomb per meter cube. Why do we discuss all these things? They have given a random paragraph with some formula. It is very confusing. So that's why I thought I will explain it. Imagine there is a wire of this shape, okay, random, and you are standing at this point and you want to find the field. What will you do? You will take a small part of the wire whose length is, let's say, dl. On that small part, the charge will be dq, and that dq by dl will be lambda, which is that property of that wire. That small charge will act like a point. So if you draw a line from that small charge to this point, you will get a small electric field arising out of it, and I will call that small electric field dE. Is it right? dE. Now there are so many such charges, so there will be so many such small teeny electric fields everywhere. Is it right? So many such small electric fields, because there are so many such charges. So small fields due to all elements. Let's say I call this distance as r. So this dE will be how much, guys? It will be Coulomb's constant into that small charge, which is dq, divided by that distance square. Now if you see carefully, Well, that dq, right? That dq is lambda into dl. So it will become k lambda into dl. Now, if I want to find, because of all the charges, how much is the net electric field? There would be some net electric field. Then that net electric field will be the vector sum of all these teeny meeny electric fields. So you will have to integrate this and get the answer. That's the whole point of this. Because you will need small elements. How do you do the elemental calculation? If it is a wire, then dq will be lambda dl. dq will be lambda dl. Same way, if it was a sheet, it will be sigma into area. So same way, imagine there is this volume. Imagine there is this volume over here. It's fully charged and I want to figure out what is the field at a point. So what you will do, you will take some random point on that surface and at this point there will be some electric field due to this unit volume that I have chosen, and that unit volume will have dq charge on it. So that dq by dv is rho. So the dq value is rho into dv, correct? And this small electric field will be Coulomb constant into dq divided by r square. But I know what my dq is. dq will be rho into dv. So when I try to find the net electric field, because there are so many small volumes, each small volume will give electric fields in different directions. So the net electric field will be integration of these small laddu paddu electric fields. So when I substitute, integration will come of that rho dv. That's the whole purpose of defining these small elements. Is this clear? Pakka? Okay, great, amazing, perfect. So that's what they have mentioned. The small electric field will be k dq by r square. dq will be density into volume, but it need not be density into volume. It could be area density into area or linear density into length, anything depending on the geometrical shape under consideration. Like this was a volume, this was a wire, depends on that. Okay, great, perfect. Now, there is no question on this. Yeah. Now, let's talk about Gauss law. This is very interesting. Gauss law. Okay, very simple and sweet this is. Imagine I have a positive charge and just visualize I take a closed surface like this, What do you think will be the flux through this closed surface? Let's imagine. Alright, what will be the closed surface flux? Flux means how many lines are piercing through it. Okay, sir, fine. So, if I visualize electric field lines because of this positive charge, it will probably look like this, maybe like this, like this, like this, like this, like this, oops, like this. I notice one very interesting thing. If a line enters, it also exits. If a line enters here, it will 100% exit here. So while entering in, by convention, flux will be negative, and while going out, the flux will be positive. So whatever goes in negative will come out positively. Net flux 0. There is no net piercing. So net flux is big fat 0, because whatever goes in negatively will be the flux which comes out positively. Interesting? Simple to visualize by this diagram. Any field which goes in has to come out. In fact, if I take any other surface even here like this, I notice even this has zero flux. Even this has zero flux. Yeah, there is no flux at all. 100% flux is zero. For the same reason, flux is zero. Oh, correct. So, sir, let's take some other area and see what do I get. Okay, let's try it out. What will happen if I take some other area? This is our positive charge. Let's choose the area maybe like this. Now interesting, guys. Flux is coming out, so positive, all the field lines are going out, so 100% the flux is a positive value. Interesting. Okay, sir. Sir, let's take another area. Now also I can see field lines exiting out from everywhere. Out means positive, so the flux has to be positive. Oh yes, correct, sir. Sir, but is phi 1 more or phi 2 more? A lot of you are going to say, sir, phi 1 is more, it is closer, phi 2 is less, it's far away. Wrong. I just mentioned when I talked about flux. Go back. I need to show you this. We discussed, oh my god, we went so ahead, huh? Okay. Where did we discuss flux? Yes, flux depends on the number of lines which pierce. So the same lines, if they pierce ahead, whether the area is big, small, doesn't matter, flux will be the same. So same concept is applicable over here. Yeah, same concept. Where is it? Where is it? Here. Same line here, same line here, same line here. So technically phi 2 is equal to phi 1. It doesn't matter what the shape is, irrespective of the shape, as long as there is a charge inside. If the charge is not inside, it's outside, the flux vanishes. Crazy, sir. Sir, can you tell me more examples? 100%. Hold on now. Look at this. I didn't need this now. Imagine there is a positive charge and a negative charge. The field will come from positive, go towards negative, positive to negative, positive to negative, positive to negative, positive to negative. Okay, correct? Looks something like this. Same field lines will come here. I'm not showing literally everything, just showing a few of the field lines. Now, just visualize if I happen to choose a closed surface like this. Oh, all the field lines are entering inside. Inside means negative. So the flux in this case is 100% negative. All field lines are entering in. Go to this place. Doesn't matter what the shape of the surface is. Notice how field lines are coming out of it. So if it is going out, it means positive. So flux at this place is 100% positive. Now it doesn't really matter what shape I take. Even if I take this shape, still it is positive because all field lines are exiting out eventually somewhere or the other. Here also it doesn't matter what shape I choose, eventually they are entering in. So as long as there is a charge inside, it either is positive or negative. But some smart dude will do like this. No charge is enclosed. Nothing like this. Here, whatever comes in goes out. Whatever comes in goes out. No charge is there inside. So whatever comes in goes out. Out is equal to in. Out is positive, in is negative. So net flux in this case is 0. Not just that, guys. Even if I happen to choose this surface, some big surface, notice whatever comes in has gone out. Whatever goes out eventually comes back. Oh, even in this scenario, the net flux is 0 because whatever goes in has come out. In is negative, out is positive. Why did this happen? Because in this scenario, the positive negative total charge inside the surface was 0. This all leads to one simple conclusion. This all has led to one simple conclusion. That is, if I have a closed surface, if I have a closed surface and there could be charges inside Q1, Q2, like that till Qn, and there could be charges outside, capital Q1, capital Q2, Q3, Q5, Qn. This flux through the closed surface only depends on charges inside, basically Q1 to Qn, and we saw that right over here. Inside charge is 0, nothing. Inside charge 0, 0. Here, inside charge is negative, flux is negative, doesn't matter what the outside charge is for this blue surface. Same way over here, outside whatever the charge is doesn't matter, inside what is there matters. Inside this surface. Here also, inside this positive was there, flux is positive. Here also, inside this surface positive was there, outside whatever is there doesn't matter, only inside matters. So flux is dependent on the charges inside and it is proportional to it, not dependent and not depend on outside Q1 to Qn charges. So what happens? We can then say the flux through the closed surface is directly proportional to the charges inside. That means Q1 plus Q2 like that till Qn, and I want to get rid of this proportionality. So Q1 to Qn, I write that new proportionality constant as 1 by epsilon naught. So that constant of proportionality is 1 by epsilon naught, which is permittivity of the medium. This is essentially your Gauss's law, nothing else. So Gauss' law says that the net electric flux through a closed surface is the charge enclosed inside by epsilon naught. That's it. It's very simple. It comes via very natural visualization. It's not an experimental law. I just showed it to you. In fact, I have proved in a way how Gauss law comes. We took various scenarios, we observed things, and we saw that yes, it always depends, the flux depends on the inside charges, never on the outside charges. Is that right? Yeah? Is this live or recorded? So what happened, Sharvesh, when I recorded this lecture, I had a time machine, and what I did was I went into the future, and in the future I saw you, yes, and I saw that you are typing this message. So immediately what I did, I again went back into my time machine. I came back, this was like some months ago, and then I told my past that listen, there will be a person at this time. So when you are recording, after exactly that much time, I took your name and I made it feel that it is a live class, but actually it is a recording. All thanks to that brilliant time machine. Okay. All right. So, yeah, this was Gauss's law. Now, before going ahead, there is one small thing which you should know. These are the charges inside. At the same time, these are the charges outside. Now, when you calculate the flux, remember you take small area vector at that particular location, you might get a field. The field can be at different angles. So when you write flux through the closed surface, remember it was an integral, cyclic integral, and it was having electric field dot the area vector, and this is equal to 1 by epsilon naught times whatever charge is there inside, not on the charge which is there outside. This becomes an extended form. Oh, thank you so much. My battery gave up on me, man. My battery gave up on me. I did not give up. Ayo. Yeah. So I have two sets of this thing. Now coming back to this, answer this question. Is this electric field due to inside charge or outside charge? Now, a lot of people think this is due to inside charge, but that is absolutely wrong. Yes, this whole term depends on the inside charge, but this is field is, this is the net field is due to both inside and outside charges, due to Q in and Q out. This is very, very important. See, I'll tell you why. Because forget the surface, forget the closed surface, forget the area, forget the flux. If you just had to find the field, what will you do? Superposition. Field due to this, everyone will give field. You will calculate the net field. Where is the question? What is inside and outside? That inside outside concept came because of the surface. Field does not understand all that. Field is the normal net field. Inside outside all the things will give field. So the funny and the irony of this entire Gauss law is This inside term is dependent on both inside and outside, but this whole term is only dependent on the net flux. Net flux only depends on whatever is the inside charge. So inside the integration, that value depends on both, but the value of the integral is independent of outside charges. It only depends on the inside charge. Is that clear? Isn't it amazing? Very interesting formula. All right. So let's use this and solve some questions. Let's start with a laddu question and then we'll take it to more difficult questions. A point charge is placed at the geometrical center. The flux passing through any single face of the cube. This is one of the most standard questions, I would say, which you can get. And see, this has come in JEE Mains 2021 and it has got repeated multiple times. So, if you place a charge at the center of the cube, you will notice the electric field will not only come up or down, but it will also come front and back and also left and right. But the net flux through the entire cube is a closed surface, so it is the flux through the closed surface, and it will be whatever charge is inside by epsilon. What is the charge inside, guys? It is just Q, so this will be Q by epsilon. That is the flux inside the entire cube. That is not even the question. Read the question. The question is something else. Through a single face of the cube. That means you take any one face. Oh, there are 6 faces. There are 6 faces. Each face by symmetry will have the same flux. This top, left, right, everything is same. So that's why I can say the flux through any one of the face is the flux through the cube divided by 6, because there are 6 faces. That's it. So it will be Q by 6 epsilon naught. Q by 6 epsilon naught is option B. Is that right, everyone? Simple, laddu, pakka? Very good. Now, there can be different varieties of questions in here. For example, look at this. You have been given, I'm not writing the question now. You have been given again a cube, but this time the charge is placed on the vertex, over here. So the question is, how much flux passes through this face? That is the question. How much flux passes through this face? Now you start thinking, now it is not symmetric. Obviously, it is obviously not symmetric. Then comes visualization and creativity. So what we do, we make a big cube of double the side length, like this. I think I'm short of. Okay, now I can't draw it completely. Unfortunately, I don't have space and I can't shift this so easily because the entire thing will get shifted. Oh, no, I have to go double the length. Like this, like this, like this, and like this. Visualize a big cube, double the side length. Okay. Now that cube is at the center of the big, basically 2 times cube, double the size. Is that right, everyone? Now if you take any one face of that big cube, any one face of that big cube, like for example this one. This problem looks very similar to the previous question which we just solved. So the flux through a face of that big cube will be 1/6 of q by epsilon naught. This comes from here. Any one face and charge is at the center, it is 1/6 q by epsilon naught. Is that right? Now the real challenge. Isn't this 1/4 of that face? Because you can clearly see there is one part here, one part here, one part here and one part here. So it is 1/4. So the flux through the shaded part, isn't it 1/4 of the flux through the face of the big cube? So it will be 1/4 of q by 6 epsilon. 4 6 are 24. So won't it be q by 24 epsilon naught? So that's the answer. Is that right, everybody? Pakka? Simple, straightforward? Amazing, amazing. Then there was another beautiful question which went on to be like this. A cylinder is there. Okay, a cylinder is there. And it is mentioned that there is a charge exactly at the center. Charge at the center. It's given. It was also given the flux through the flat circular face. Flux through the flat circular face is phi. Question was, how much flux is there through the curved surface? This was the question. How much flux is going through the curved surface? That is the question. Interesting. So what we need to do, let's understand. If you take the entire cylinder is a closed surface. So if you take the entire cylinder, that cylinder is a complete closed surface and that flux is q by epsilon. Correct? Okay. Now that cylinder's entire surface is made of multiple surfaces. One circular face, another circular face over here, and the last one is this one, which is the curved surface, which you can see. This is the third one. Three surfaces together make the entire cylinder. So can I say the total flux of the cylinder is flux through the curved surface, and there are two such circular faces, so 2 times the flux through the circular face. But the circular face flux is given to be phi. So this is equal to your q by epsilon naught, and what is asked is exactly how much is the flux through the curved surface. So flux through the curved surface is q by epsilon naught minus 2 times of phi. Minus 2 times of phi. That's the answer. Is that clear, everyone? Yeah. Very good. Very good. Amazing. Oh. This is a known bug. Whenever I shade something, the board hangs. It will take some time. I'm scared. Whatever I written till now should not go. Yeah, man. See these loafers. Again, what is this? Money more. My God, you guys don't understand sarcasm. When I said I will go to Himalayas, you literally thought I will go to Himalayas. Guys, you don't know me, yeah? You don't understand my jokes. My God, literally, guys. I have to spoon feed you everything now. No mind change, nothing. It was very clear where I am going, what I am doing. My God. Really, guys. I was expecting slightly better from you guys. Okay, this is done. Cool. Anyways, then one more question over here. There is a charge of 2 coulombs, minus 3 coulombs, minus 1 coulomb, plus 4 coulomb, plus 7 coulomb, minus 0.5 coulomb, plus 0.9 coulomb. And there is a Gaussian surface which is drawn something like this. Okay. The question is, what is the flux through that closed surface? By the way, the closed surface is sometimes also called as a Gaussian surface. It's just a name given to any closed surface. It is also called Gaussian surface. Okay, so how do I figure this out? As you can see, it's a closed surface. So for that, using Gauss law, it will be Q in by epsilon naught. What is the total charge inside? Just calculate it and divide by epsilon. So charges are 2, minus 1, minus 3 by epsilon naught. So it will become minus 1, minus 3, minus 4. 2 minus 4 is minus 2. So minus 2 by epsilon naught. What does this negative sign indicate? Negative indicates that net flux is inwards. So most of the field lines are going inside rather than outside. That is what it means. Simple? Okay, good. Now that we have understood what is Gauss law, all these pointers are there. Just go through it once. It is there in your NCERT. It's very simple. Gauss law is true for any surface, obviously, not just circular. True. The term on the right hand side is the sum of the charges within the surface. It can be located anywhere inside. It doesn't matter where that charge is, as long as it is inside, you are sorted. If the surface is chosen in such a way, some is inside, some is outside, the field is because of both inside and outside, which I just mentioned some time back. Then surface you choose while applying Gauss law has to be chosen conveniently. Now we are going to learn application of Gauss law, like where do you apply Gauss law? In there, how do you choose the Gaussian surface? At least till now we were given the surface. Now you will not be given the surface, you have to think how to apply it. So you choose it in a convenient way. And the convenient way is such that the calculations are easy. That means you will choose a symmetrical surface like cylinder, sphere, cube, cuboid, like that. Don't choose complex. And preferably try to keep the field perpendicular or parallel to the surface. It makes the calculations easy. That's the thumb rule. And Gauss law is inverse square law, and inverse square law is Coulomb's Gauss law. We can prove it, and that's what I'm going to show you next, this 6th point. Okay, so let me show that to you in application of Gauss law. Okay, I don't have space here. Look at it. Let's choose a point charge Q, and due to a point charge, the field is radial. The field is radial. And let's say my interest is at some distance of r, I want to figure out how much is the electric field. I want to figure out how much is the field. Like, what, sir? Don't you know this already? KQ by r square. Correct, I know this, but because I know Coulomb's law. But can I get the same thing using Gauss law? That's my whole purpose. So let's try it out. Fair enough. So let's start. Let's take a point charge. let's visualize how the field will look like. I know the field is radial, so I will show radial field. It's going to be actually spherical in nature, something like this. Ooh. Okay, this is the radial field like this. I said while applying Gauss law, choose a nice surface, symmetric surface, field is parallel or perpendicular. Now it's very obvious what kind of surface you will choose. No brainer, it has to be spherical. Correct? So choose a basic spherical surface. This is spherical in nature. Okay? This is a spherical, closed means Gaussian, spherical Gaussian surface. Yeah, spherical Gaussian surface. Perfect? Good. Okay. Now what now? See, most of the places the field is perpendicular, which is in a way good. I'll tell you how. You take any element, let's say for example here. That small element will have an area vector, which will be dA, and at that place the field will be E. Everywhere area vector and field are parallel. So the field is parallel to my area vector everywhere on that Gaussian surface. It is very important that this happens while I am applying something, some trend should be there. Now, if I apply Gauss's law, let's start. Flux through the sphere, which is a closed surface, will be whatever charge is inside by epsilon naught. The charge which is inside is obviously Q, you can see that, divided by our epsilon naught. What is the flux on the surface? Oh, interesting. Cyclic integral, electric field dot my area vector. Now see, this is what the interesting thing is. Everywhere it is parallel. E dA cos 0, E dA cos 0, E dA cos 0, cos 0, cos 0, cos 0. Everywhere it is 1. So this dot product will become dA into cos 0. Yes, of course this cyclic integral is there. But even before doing that, this field, same distance, same gap, same density, same compactness. So field value is same. So electric field can be taken outside. It is constant, same value. So cos 0 is 1, perfect. So let's just write this as Q by epsilon naught. So my field is outside, and inside this I have just one thing, which is integration of dA, and here I have Q by epsilon naught. What is integration of dA? Area add everywhere. I am adding the surface area of the sphere, which is 4 pi. Oh, I didn't give the radius. Fair enough. Let's take the radius as r. How does it matter? 4 pi r square. This is Q. Oops. Q by epsilon naught. Wow, sir. Now what? What are you trying to do? Are you trying to do some magic? Yes, I am trying to show you some magic. Just bring these gentlemen here. Just bring these people over here. Electric field will be Q by 4 pi r square epsilon. Sir, I didn't see magic. You didn't see magic? I'll show you now. Look at this. Electric field is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, correct, Q by r square. Oh sir, this is nothing but Coulomb's law. This is nothing but Coulomb's law, because force you will get from this, force is charge into field, so it will become 1 by 4 pi epsilon naught Q by r square. It's Coulomb's law only at the end of the day. And don't say, sir, this is field, force is this. Understand, concept. This explains why 4 pi multiplies with epsilon. It comes because of Gauss law, nothing else. Got it, everyone? Yes? Everyone? Clear? So, lot of people have this question. Why even 4 pi? Why 1 pi? That pi came because of this derivation. So, this point which is there, Gauss law is based on Coulomb's law, and Coulomb's law is based on Gauss law. Any violation in one causes a violation in the other. So, Gauss is not independent of Coulomb. It's the same. It's just a different way of writing it. Because if Gauss were not true, I couldn't get this. If Coulomb were not true, I can't reverse calculate to Gauss law. Either one of them. Got it? Yeah. Nice explanation, Praveen. Got it? Amazing. Very nice. Now let's apply Gauss law to multiple other geometries, and starting off with this one. Remember, we talked about charge distributions here. This centipede out here, this surface, my god, it looks like a strawberry, isn't it? I somehow feel it's like a strawberry, and this also looks very attractive. It feels like one fruit which I should just grab onto, or it also feels like something which has got diseased, some disease, some pimples, or some weird chicken pox it has got. Anyways, yeah, so I spoke about these geometries. We are going to use these geometries. Why not? Let's go down over here. Now, so if you have a very long wire and you want to find what is the field around it, visualize this. This is a very interesting visualization. The field around it will be radially outwards. Nothing will pierce like that. Oops. Nothing will pierce like that at an angle. Everything will be perpendicular to this wire basically at every point. Yes, everything will be perpendicular to that long charged wire. So if I want to find the field, try symmetry. It's a long wire, field is radial, cylinder, only cylindrical surface makes sense. I don't think cube, cone, sphere also makes sense, because sphere will be limited in height. This has to be infinitely long. So it's a cylinder, not necessarily infinitely long, some height is there. So assume this is my new Gaussian surface. This is my Gaussian surface. Gaussian surface. Height is h, radius bro is r. Okay, take it. Now let's start solving it. So what do we have? What do we have? What do we have? Field at this point is E. And notice one interesting thing. Everywhere along that surface, the constant value of field will be there. Everywhere. Not just there, even here. Because same distance, same distance, same distance, same distance, same distance, same distance. So field on the surface is same. So on surface is same everywhere on the surface of the cylinder. Start with Gauss law. Flux on that cylinder, flux on the cylinder is charge which is inside by epsilon naught. Now, interesting. If you see the cylinder, inside of it, only a small part of the wire is there. The wire is infinitely long, but only a small part of the wire is there inside the cylinder. And we know there is a parameter called lambda, which is charge per unit length, So if I take this much length, which is height, which is basically the height, that will give me whatever is charge inside. So whatever charge is inside is there inside that height. So Q in is basically lambda h. Visualize that. Okay, that is the first thing. So Q in, I'm just going to put lambda h. Perfect. This is epsilon. Now for the flux of the cylinder, two important points. This surface and this surface do not contribute anything at all in the flux because no line is piercing it. So the flux through the cylinder is only the flux through the curved surface. Why? Because there is no contribution from circular face. How much is the flux on the curved surface? Okay, not a big deal. Cyclic integral electric field dot dA vector. But this dot product, believe me, will again be, because of cos 0 being 1, will be much easier. Area vector is parallel to the field everywhere. So the dot product will have cos of 0. You will have dA over here. Cyclic integral also will be there. And best part, this electric field is just going to come outside. Why? Because it is a same value everywhere on the surface. So constants go outside the integration. So E is there and I am left with integration of just dA because cos 0 is 1 and this is lambda h divided by epsilon. What now, sir? Add areas. Only curved, not anything else. Only curved. So the curved area is 2 pi RH. 2 pi r is the perimeter. 2 pi r into h is curved area. So just put 2 pi r h. Great. This is electric field. This is lambda h and this is epsilon. Interesting. H goes off. What do we have? Electric field is lambda by 2 pi r epsilon. Not a right way to write it. I don't find it convenient like this. So E will be 1 by 2 pi epsilon naught and into lambda by r. It is inversely related to r. This looks good. Instead of 1 by 4 pi, it is 1 by 2 pi epsilon naught. Yeah? Yes. Very good. Okay. All right. Okay. Amazing. And that is what you have to remember. Where did we go? Here. So the electric field is lambda by 2 pi epsilon naught r, radially outwards. This formula, please remember it. If you want to remember this, or is the same thing, one and the same. What is lambda? Charge per unit length. Okay. What kind of question can come? I think I have a question on that. An infinitely long wire produces an electric field at a distance of 2 linear charge density lambda of that wire. Simple, guys. See, this was asked in 2022 year, direct formula application. So for a long wire, we know electric field. 1 second, guys. It's acting very weird. Let me just save this file before something gets damaged, so that at least whatever I've done is there. Students are not chatting rubbish. Oh, who will chat rubbish here now at this point of time? You need real big enthu for chatting rubbish now. Evening time, all the lovebirds are active. Now night time, I think very rare. And also JEE stuff, listening to it only very, students only will not understand. Yo, what is this happening? So kids will go to some place where more boys and girls are there, no? So where people can mingle, find new people, right? So that's the reason, man. Okay, but when JEE exam comes close by, you have all sorts of nonsense happening. Anyways, coming back over here, linear charge. What is this? 1 by 2 pi epsilon naught lambda by r. We want to find lambda, right? So what is this value? I have an idea. Why not multiply 2? Basically write this as 1 by 4 pi epsilon naught and then put 2 lambda by r. What is the reason for this? I know this value, and electric field is how much? 9 into 10 to the power 4. This value I know is 9 into 10 to the power 9 into 2 lambda, I don't know, r centimeters, 2 into 10 to the power minus 2. Okay, what is there? 9, 9, bye bye, 2, 2, bye bye, 10 to the power 4, this will become 5. This will go on the top. Okay, fair enough. So 1 is equal to 10 to the power 7 into lambda. So lambda will be 10 to the power minus 7. So this will be 0.1 into 10 to the power minus 6. Minus 6 is micro. So 0.1 micro coulomb per meter. 0.1 micro coulomb per meter. That is this answer. Is that right, everyone? Option A. How many of you got it? No, man, I'm not Mallu, but I have a lot of Mallu friends. Yes. Cool. Okay. Let's see what happens in case of a flat sheet. Just a sheet of paper. Just imagine this. This particular mouse pad is charged. What will happen? This charge everywhere will give a field here also and back side also. Back and front. Both sides field will go. That's exactly what is happening. And you can take a Gaussian surface just like the one shown over here, like again a cylinder or even a cube will do, even a cuboid will do, by the way, and even a non-cuboid will do, but it has to be symmetric on both sides. So this sheet has a charge density sigma, which is how much charge is there per unit area. The funny thing about a large sheet is that it produces field on both sides which is uniform in nature. Yes, this side or even this side, this field is uniform. Uniform field. Why is it uniform? Because the spacing is the same. Same gap between both of them. That's why it is uniform. So again apply Gauss law. Same way, flux through the closed surface is whatever charge is inside divided by epsilon naught. Flux is field dot area. But interesting thing here is exactly reverse of the previous question. Notice how the flux is there here and it is there here. In fact, it is absent on the curved surface. If you see the curved surface, that's where the flux is not there, guys, because the field is going like this or like this. It's not coming through the curved surface. So when you try and measure this flux, it will be only through the circular surface. Circular faces. There is no contribution from curved surface. There is no contribution from the curved surface this time. So when you try and apply this Gauss law, again the field is constant everywhere. E will come outside, and then again you will have integration, and then you will have area, and then you will have cos of 0. Why cos 0? Because again, if you take any small area vector, you will see that the area vector is parallel to the field. Parallel means theta is 0. Okay, perfect. So cos 0 is 1. So just integration of area is there, and then you will have field over here. That's also okay. What happens to the right hand side? Notice how inside the cylinder there is a small, I don't know how to show it over here, but only this much part has charge on it. This much part is the charge which is inside. So that charge, which is Q in, will be inside that area A. So the Q in will be sigma into A. So that Q in will be sigma into A. What is that A, sir? A is basically this area, the area of the circular base, area of the circular face is that area A. So sigma is charge per unit area. So if you take this charge, it is this area. If you take that charge, it is that area. So if I am taking this circular face, it is the circular cut area from that big plate, it is that charge in that circular area of that cut plate, okay, or imaginary cutting, it's not a real cutting. Okay. Now what is this going to be? See, electric field is as it is. What was this, guys? It is the area of circular faces. There are two faces, so do not forget to write this as 2 times of A. Both the faces contribute in the flux. Curved does not contribute. So this will be equal to your same thing, sigma A by epsilon. What happens now is that this area and this area gets cancelled, and you will notice that your electric field comes out as sigma by 2 epsilon naught. Sigma by 2 epsilon naught. So this is the final formula. Sigma by 2 epsilon is the electric field due to a charge sheet. All these are applications of Gauss's law. All these are applications of Gauss's law. Simple. Correct? Thank you, Ranjit, for all the love. Very good. Now the third application is a shell, and for a shell you are outside or inside. Shell means just a hollow sphere. The charges only are there on the at a distance of r from some center. Nothing else. Nothing is there inside nor outside. What happens is, in such a shell, you will notice anywhere inside the field is 0. Yes, anywhere inside the shell, the field is 0. Why? Means if you take any Gaussian surface here, notice the flux through any closed surface will be 0. Reason, charge inside is 0. Inside this surface, there is no charge, because whatever charge is there is here, which is outside. So because of that, Q in being 0, flux is 0. And because our flux is 0, think what will happen. Integration of E dot dA will be 0. How can this integration be 0? Not because area is 0, area is there. There is only one reason why this is 0, and that is because electric field is 0. So inside a shell, everywhere the field is 0. That's the outcome of this. And what happens outside? If you go outside, then this formulation is very similar. You take a Gaussian surface like this. You take a Gaussian surface like this. You take flux through the sphere, and you will notice whatever charge is inside is actually the entire charge of the sphere here, the actual shell. So the entire charge of the shell is inside my surface, all of it will come, and this flux will come out to be E multiplied by 4 pi r square, which makes it 1 by 4 pi epsilon naught Q by r square. This is exactly like a point charge. This is exactly like a point charge, which means this. If you have a shell and the shell is charged, if you have a shell and the shell is charged, let's say this is the radius of the shell. If you happen to be anywhere inside, if you happen to be anywhere inside, then electric field always is 0 if your distance from the center, is less than r. So inside field is 0. But the moment you decide to be outside the shell, there is field. This electric field is kq divided by r square. The moment r is more than r outside, it means it behaves like a point charge. Very interesting. It feels as if all the charge on that shell is accumulated at the center, and there is a point here, and you are finding the field, just like how you do for a point charge. There is no difference. Usually in JEE, they also end up asking this graphical questions. So you might have the field and the distance, and it looks something like this. As long as you're inside, it is 0 till you reach this r, which is the boundary of the shell, and the moment you go outside, it follows this law, which is inversely related to r square, immediately outside. So this is how the field versus distance from the center graph looks like. Okay, it's 0, suddenly bumps up, and then comes over here. Straightforward. There's a question, I think, hopefully on that. Yeah, I think we have it over here. Let's see, how do we do it? A thin shell is given a positive charge. The variation of field as a function of distance from the center is best described by direct formula based question. What else is there? Nothing is there in this. Come on guys. 0 for inside, outside 1 by r square. Isn't it very direct? Direct formula. Just imagine, it's exactly this. Inside it is 0, outside it is that. Exactly the same formula. So this direct question has come in JEE Mains of 2023. Yeah, straightforward. Yeah. Very nice. Now, how can you get some more tricky questions? Imagine this. You have been told there is a sphere here, there is a shell here, shells like this. Let's say this is q, let's say this is minus 2q, or let's say minus 3q, or you can take it anything else also. Let's say this is 3q. In each region, can you figure out what is the field? That could be a question. Find the fields in each region. Let's start one by one. Let's go to the innermost region. Starting over here. Oh, by the way, they need to also mention what's the radius and all of that. Let's say this is r, let's say this is 2r. Now, if you are at a distance from the center which is less than r, that means in the innermost of the shells, think due to this shell there will be no contribution. You are inside that shell, you are also inside the outer shell. So basically you are inside both the shells. That means the electric field must be 0. No doubt about it. Anywhere here, field is 0. Undoubtedly. Correct, sir. Got it. Now, let's go to the next. Let's go to this is 2r. Now, let's say you are present in this region. You are now present in this particular region, which is the gap between these two shells. Now what will happen? Now what will happen? Basically, you are more than R but less than 2R. Because of the outer shell, since you are inside of it, there is no contribution. You are inside the outer shell. So the contribution will be zero field. So there will be no field because of this shell, because you are anywhere inside of this shell. But you are outside the inner shell. So it will behave like a point charge. So when I am here, this shell will behave like a point charge and the field will be K, this charge Q divided by R square. No other person will come, no other contribution will come, because that outer shell has no role to play in this. Correct? Yes? Very good. Now, finally, we go completely outside. We go basically completely outside. That means my distance is more than 2R. Now, since I am outside, both the shells, that means both of them are going to behave like point charges. It feels then as if this Q is condensed over here, this 3Q is also condensed over here. Together we have 4Q charge, and then from that 4Q charge you are at a distance of R. You are at a distance of R from that 4Q charge. So at this particular point the field will be K multiplied by 4Q divided by R square. Right? That's how the fields are in different regions. Innermost region, nothing. You are inside both of them. In between, you are outside the inner one but inside the outer one. So the outer one will not contribute, inner one will contribute. And lastly, when you are completely outside, then both the shells will compact into a single point charge as 4Q, and then you can treat it like a single point charge. Yeah? Everyone? Yeah? Okay, great. Now, we have done mostly everything, but one last thing over here. This can be particularly useful for your JEE Advanced, very rarely JEE Mains, but still it's my duty that I give it to you. If you have a uniformly charged sphere, this is very interesting. If you have a uniformly charged sphere, okay, so the charges are not just there on the periphery but also inside. So uniformly charged sphere. See, when it's that kind of situation, it's very simple when you are outside, because when you are outside, the electric field will be as if all the charge is concentrated at the center only. So it will be just K capital Q by R square. So outside behaves like a point charge. There is no doubt in that. The problem happens when you are inside. Then it is no longer 0, because a lot of students make this mistake. They write it as 0, wrong. At this point, the electric field, this electric field comes out to be KQ. Here you have this radius of the sphere cube, yes, cube of the radius. So to compensate that dimensionally, you write small r over here. That's it. So this is the formula. When you are inside, it is linear to the distance. It is linear to the distance. Meaning, if you had to plot the graph of the electric field versus the distance, inside it is proportional to r. So you will see it goes up like this. Outside it is inversely proportional to r square. So it comes back like this. Inversely proportional to r square, and inside is directly proportional to r. And this transition happens where? Exactly on the boundary, that is radius capital R of this solid sphere. Okay, it's a solid sphere which is charged, not a hollow one. That's how the graph looks like. This is also very important geometry which you should know. Cool? That's all. So we are done. Yes, we studied flux. We have also seen Gauss's law and all the three formulas: linear, surface and spherical shell. In fact, we did complete solid sphere also. Now I want to know from you, are you going to be regular? Are you going to be sincere? Are you going to talk about these sessions? Are you going to talk about Shreyas Sir? Are you going to talk about PWJ English? Are you going to talk about the physics classes? Are you going to talk about chemistry, maths classes? Are you going to talk about these JEE classes with the help of NCERT and JEE questions combined? Everything, so that in detail we are learning. I want full support, full enthusiasm, full sincere attendance every day. Ready for it? Every day, or basically every week, you are going to have, if you want these kind of classes, you need to put it up. Okay, so I wanted to start your JEE journey with NCERT, so at least you will get that kickstart. A lot of students had this backlogs in the first two chapters, so I thought I will conduct these two chapters. So today we done chapter 1, chapter 2, maybe I'll do next week. Cool. So I hope you enjoyed it, and thank you. Put down comments. Are you ready? Did you enjoy? Put a heart, say hi, just tell where you are from. Vanakkam, Endariki Namaskaram, Ellaruge Namaskara, Sagranda Namaskar. Yes, everybody doing great. Yeah, just put up some nice comment. Shubhamanu. Yep, good. Thank you so much. Bye.